Hello friends, in this video we'll be learning Turing machine and undecidability. This is the last topic in theory of computation, but which will have the good weightage in GATE exam. You could predict a 2 to 4 marks only from this topic, and that too theoretical questions. That means you don't need to worry much about Turing machine construction. Like in PD also, we don't worry much about construction, but you should know about identifying the languages and knowing the important concepts of the pushdown automata as well as Turing machine. Okay, let's begin the topic Turing machine and Decidability. Believe me, the questions, the concept that I cover in this topic as well as in pushdown automata, which is purely related to the GATE exam point of view. That means if you feel something which is less covered, then understand what is important for GATE exam. So based on my experience, I am going to cover the concepts which are really required for the exam. But if you really wanted to learn the theory of computation, this Turing machine topic will take days and months. So that's why I'm talking about what is important for the GATE exam. Okay. If you look at the whole theory of computation, we have started our journey from regular expressions, and then we have moved to the Turing machine and undecidability. So every stage you have learned something new in the theory of computation. Like in the first three topics, we have learned what is regular language, how do you identify it, how do you represent it, right? All the things you have learned in these topics, and what are the operations you can apply over the languages. And grammars, a very special topic for you. You will predict, or it is also important for the compiler design. That's why we have learned separately the regular grammars and context-free grammars. Then we have seen a very interesting topic, that is PDA, CFL and dcfls. Of course, the context-free grammars along with this is a complete topic for context-free languages, right? Here you have learned how to construct the PDA and then how to identify the dcfl, CFLs, and also closure properties of CFL, dcfls. All the three are related to the context-free languages. Then finally, we are going to stand here. What is Turing machine? What are the properties that you see for decidability and undecidability? Okay, let's move to the Turing machine. My first question is, what is Turing machine, right? The Turing has invented a machine, but is it really important for us? In daily life, the Turing machine gives you something which is going to compute whatever it is. You have something, and for that you have a logic to compute, or you have understood the problem and you have something to compute. Then we say you have built a Turing machine. Then the Turing machine need not be particular restricted model. You can change the Turing machine definition, but it should be so powerful to compute in this world, right? If you look at the finite automata, pushdown automata, linear bound automata, Turing machine, the Turing machine is more powerful in the world. In the sense, anything you have a problem, and for that you have a solution, that means you have a Turing machine. So understand today how do you compare this Turing machine into the reality, right? That's why I'm talking about in theory of computation. Whatever you have learned so far is to just gain the knowledge of basics of TOC, but when you know what is Turing machine, that you will definitely understand what is theory of computation, right? So the Turing machine is more powerful and that can express all the computable languages or problems in the world. That's why we have the Turing machine. Simply you can call a machine that is going to represent your language if it is computable. Let's talk about what is Turing machine. Turing machine is, you can call automata, which is going to represent or accept, recursively enumerable language. Turing machine can be designed actually two ways. It can, or it represents, you can say, accepts recursively enumerable language. Or E, you can also call or E, recursively enumerable language or set. I use the REL but you may also use RE. Both are same, recursively enumerable language or recursively enumerable. Simply, when I say language is recursively enumerable, we use RE or REL. Both are represent the same here. Now, what else you have apart from this? Turing machine you can also design to enumerate. It enumerates. If you really want it, it can enumerate. But the way you design will change for acceptance as well as enumerating. Enumerates REL. So what is an REL? Recursively enumerable language. How it accepts, how it enumerates, we'll see that slowly. Now, what is the definition of Turing machine? Like you have a finite automata, push down automata. Of course, linear bound automata, we will come to that later. Now, what is the definition of Turing machine? If I say what is the definition of finite automata, you can simply say if the string is valid, it definitely halts at a final state. If it is deterministic, it will take exactly one path. Similarly, do you have any definition for the Turing machine? Similarly, so I'm going for acceptance. How it going to be defined? Mainly, we will focus on acceptance now. Okay. Suppose TM that is accepting language L. That's L is recursively enumerable language. Remember this, whenever TM accepts L, it could be finite language or regular language or context-free language or deterministic, context-free, context-sensitive, recursive, but everything is called as recursively enumerable language. It's a very important machine where it can be used for all the classes that you have seen so far. Now, you may give some string, let's say W. In case if W belongs to L, if W belongs to L, what happens? What happens in finite automata, push down automata, or linear bound automata? False at final. Of course, will it take exactly one path or at least one path? That depends on nature of the machine, deterministic or non-deterministic. So I'll just say halts at final. I'm not talking about how many paths. Okay, halts at final state. Definitely. Okay, if string is present in the language, Turing machine should accept. It will say that I will halt at final if the string is valid. If I am the deterministic machine, definitely I will have exactly one path. If I am the non-deterministic machine, I can guarantee at least one path. That halts at final. Now, the main important point here, if the string is not belongs to language, suppose Turing machine is not accepting that string, then what is the behavior of the Turing machine? Think about it. What happens to finite automata? If the string is invalid, it halts at non-final, right? It halts at non-final. What is the push down automata behavior? Same. The string is invalid, it halts at non-final. Maybe 0 paths, but that's okay, but still halts at non-final. Now, what is the behavior of this Turing machine? Here you have two cases. Either halts at non-final, state, or never halts. The Turing machine may go to a situation never halts. Okay, there are two situations may happen. The string is invalid. The string is valid, definitely it will halt at final. Okay, it will halt at final. The string is invalid, either it will halt at non-final or it never halts. This is the main behavior of the Turing. Right? Why we do this? Because to understand the computability power of the languages or problems, to know what problems are computable. Suppose I want to travel from one place to other place. You will think about only that direction, right? I want to go from this place to other place. You will not think about going to other places. That is why you should know what are the valid strings that you can accept. What is the logic for the valid strings? That is the most important when you solve any problem. Like I want to compute or I want to produce the prime numbers. The logic should be there for prime. And do you want to produce non-prime numbers? Then that is a secondary case for us. Okay, you may do it, but it is a secondary case for you. Always remember, whenever you are designing Turing machine or somebody is given to you, main focus goes to this. Whenever the string is valid, it should halt at final. The string is invalid, really you are in danger, because it might halt at non-final, or it might be the case never halt. Like your programs, you are expecting to find, let's say, prime number. So every time you are giving, let's say, positive number, your program is halting. Somebody is given negative number, your program may go infinite loop, because you are thinking only the input is given as a positive number, so your loop is working fine. But somebody is given negative number, your program may not work because that is invalid string, you may not be taken care, so it might be the situation you may go to never halt. So this happens when you don't want it, that's not there in your language, you have not covered in your logic, then this situation might arise. But anyhow, still you have done good job, because you are able to understand all the valid strings in the language. Okay, this is about the Turing machine. Whenever you want to understand the Turing machine, believe me, only 2 points to remember. If the real string is valid, it should halt. String is invalid, really we don't know, it might halt at non-final, or it never halts. Okay, let's move to understand more about the various machines that we are going to learn. See, people might think the Turing machine, halting Turing machine, linear bound automata are actually completely different, but not exactly. All the three you can say Turing machines only, but based on its behavior, it's going to change its definition. Like, first I'm talking about Turing machine. When somebody is asking about Turing machine, simply say always halts for every valid string. That's all you need to remember. You don't need to worry about the remaining. Invalid strings, I am not saying always, it may or may not. For every valid string, Turing machine is going to halt for every valid string. Okay, that's the main important criteria of Turing machine. Using this, when I put more and more restrictions, then you are going to get other things like halting Turing machine. Doesn't matter string is valid or invalid. In case if it is going to halt all the time, then that Turing machine is halting Turing machine. It halts, simply you say that always halts. That's it. Whether it is invalid or valid doesn't matter. For both valid and invalid. For both valid and invalid strings. Simply every string. I can say for every string. You don't need to say both valid and invalid. Simply say for every string. That would be sufficient. Okay, it's going to halt for every string. Then what is this linear bound automata? When you are going to talk about HTM, it is a TM that always halts for every string. Now I can say that it is TM that always halts for every string. What is LBA? It is HTM. That means it is going to halt all the time. It is a TM, it is HTM that always halts for every string. But what is this LBA? It's going to use the memory, the tape, that linearly bounded. You don't use exponentially. To understand the given input, you may use additional tape length, but that's linearly bounded based on your input. So here the tape, it is HTM, but tape length is linearly bounded. You do not use infinite tape here. Depends on your input length, it is going to be bounded. In both of them, HTM and TM, you can use the tape because its tape is infinite. It's unbounded basically. Here in LVA, the tape length is bounded, the linearly, that too based on the given input length. This is a very important point. How much tape you use, it's the name itself says linearly bounded automata, right? Do not assume that your tape is unbounded, right? Even though it is unbounded looks like, but you have to limit based on your input length. So the main differences, and you might aware that what LB accepts, context sensitive language. What HTM accepts? Decidable language. You can also call recursive language. What is another name? Decidable. Very powerful name. Recursive language. There are many names for this. And what TM accepts? RE language. RE language. Okay. So the three important machines that are all actually depends on Turing machine definition only. Okay. Next. Now we are talking about a definition of Turing machine and comparison with other machines like HTM and LBA. But what is the configuration of Turing machine when you compare with finite automata and PDA? Okay, let me tell you what is a finite automata. The finite automata is going to have 5 parameters. You might aware of all this, right? And what is the push down automata, which is more important? Q, sigma, del, Q naught, F, and other things we have seen, Z naught and gamma. 7 parameters. In PDA we have 7 parameters. What is Turing machine? What is Turing machine? The configuration is similar to the finite automata, but here you may use one-way tape or two-way tape. That's your choice. I'm keeping head here. The whole tape has blank symbols by default other than your input. That's input tape. You have the same as finite automata like finite control you have here. Now the head is in both finite automata and PDA we are reading the input from the input tape, but here you have read or write head. You have the multiple features for the same head. But this was input tape in both finite automata and PDA, but here it could be input or output tape, but simply you call it as a tape, because you can read and also you can write onto the tape, depends on the requirement. Now we have a tape and we have the head is bidirectional. You can read or write from this bidirectional tape, right? The bidirectional, you can move either left or right. Bidirectional tape. Now you tell me, well, how many parameters are there? How many parameters are there? The parameters here additionally, like compared to finite automata, additionally you have the blank symbol, another one is tape alphabet, 2 additional parameters. Let me write them. Turing machine is having almost same as a finite automata, but additionally 2 parameters. What are they? One is blank symbol, other one is tau, represent tape alphabet. This is a blank symbol which is there in entire tape other than your input. Blank symbol. The tau is called as here tape alphabet, like stack, input, you have a tape now. In PDA we have 2, they are Z naught is the bottom of the stacks for the stack symbol, and gamma is the stack alphabet. Here you have tape alphabet and blank symbol. So what is the use of this tape alphabet? Already we have a sigma, this is the input alphabet, right? Then why do you need this tape alphabet? In finite automata and PDA you are not writing the sigma and the tape alphabet and input alphabet, there was no difference. So you did not maintain separately, as you are not writing ever into the tape. But now if you want to remember it, you may write this symbol with X, or you may write this symbol with Y, something like this. Then what's happening? Actually sigma is A comma B, but now tape is something different. Like it is already having a blank in this tape, and A was there, B was there at some point, and now X and Y also came. This tau is going to say the tape alphabet, where all the symbols that appeared on the tape should be maintained in the tape alphabet. Okay, if any symbol which is not there in the tape alphabet, it should not use to write onto the tape. Okay, that's the rule here. What is the difference between sigma and tau? Sigma is subset or equal to tau. And what is the blank? Blank is a special symbol that belongs to tau. Okay, these are the 2 points you need to learn. And what is this delta? Right, del or transition function. You have 2 types of motions: DTM, deterministic Turing motion, non-deterministic Turing motion. Remember, like DFA and NFA, these 2 motions are also equivalent. You can convert one to other. So if you want, you can also remember this DTM and NTM are equivalent, because if you can design DTM, you can also design NTM. If you can design NTM, you can also design DTM, like DF and NFA concept. Now in the DTM, what is this delta? What is this delta? See, earlier you were using infinite automata and push down automata Q cross sigma, right? But now the sigma you may not see all the time in the tape. You will see actually sometimes XY, sometimes AB. That means which is the best alphabet that you can use? That is tape alphabet, in which symbols are there. That means input symbols are there, and also the new symbols that you have written, both are covered in the tau. So tau is going to be the best option for both Q cross tau. Okay. Now that means from any state, by reading the tape symbol, you don't have 2 places like stack. Stack you have to read, at the same time you have to look at who is at top of the stack. Then you can take the decision in the PDA. But in Turing motion, just from the present state, what is the current tape symbol that you are reading? Because input symbol already gone, right? Now we don't consider the only input, because here X and Y are actually not input symbols, but still some state can read them. So tau is the best option. Now if it is a deterministic Turing motion, you will go to some state, you will write with some symbol, and then you will move either left or right. Right? It's very easy. You are reading something and you will write with something, but you will move either left or right. Sometimes you will stay there, then you have to add left, right, and stay there. Right now, this is the DTM definition. What is the NTM definition? The same thing will happen non-deterministically. Q cross, tau cross, left or right. Okay. This is about DTM and NTM. Obviously, it takes time to understand what is this transition function. But at this moment, I hope you are aware of all these parameters. Q represents set of states, and sigma represent input alphabet. Delta represent either DTM or NTM. And here Q naught is initial state if a set of final states, which is a blank symbol which is there throughout the tape if you don't write with any other symbol. And tau is the tape alphabet. All the symbols that you push pop from the stack, or all the symbols that appear on the stack will be there. Oh sorry, there is no stack, right? This is what happens sometimes. You were there in PDA, now you came to Turing motion, see that my brain switched automatically to the push down automata. So now you should worry about it. When you are using this terminology, be careful, are you using tape or stack? Because symbol looks same, but that is a gamma, this is a tau, but in some textbooks they use gamma in both the places. Then this tau doesn't represent stack. So what does this tau represent? All the symbols that appear on the tape. Don't say that all the symbols which appear on the stack. Okay, small change, that mistakes. Tau represent tape alphabet, where all the symbols that appear on the tape, including input symbols, including blank symbol, will be there in the tau, which is a set, which is the alphabet. Okay? So now TM configuration, but still there is a lot to learn about the construction. We'll move slowly the Turing motion. Before constructing how Turing motion can be designed, it's not only designed for acceptance, it's not only designed for halting, It's and also not only designed for enumeration, it could be used for various purposes. But mainly we are looking at here three things: how the machine is designed, and how the machine is used to accept, or how the machine is enumerated. So when the machine is designed, let's say halting behavior, TM, let's say halts on, let's say A star, then what happens? Whenever you give an input, let's try that. If I am giving, let's say double A, what it should do? It should say halts on double A. Suppose whenever I give an input, let's say AB, it should say does not halt, because it only halts on, does not halt on AB. This is what happens. Already Turing machine designed to halt on A star, but is not halting. It doesn't matter, final, non-final. Here there is no final, non-final concept. The main focus is on halting only. Halting, that's it. Whenever the particular string which is there in your language, that means I'm going to halt. But it's not in A star, it's not going to halt. Does not halt means your head will move sometimes left, sometimes right, or sometimes right, sometimes left, or it will move forever only one direction. That never halts. It could happen, right? The TM also on A star, if you have designed that machine, whenever the string you have given from A star, it will halt. If you don't give from A star, it will not halt. This is the one behavior of the Turing machine designed to halt on a specific reasons or specific requirement. Now second one, acceptance. You already know acceptance, right? TM accepts, let's say, A star. This is different completely. You can't design the same way like you did above. In this, there is no final, non-final concept. It will all, that's it. There is no final, non-final concept in the first type. Second type, when you give a string, let's say double A, it says double A accepts. Then how it accepts? This Turing machine will definitely halt at final. Halts at final. Don't say simply halt. Halts at a final state on double A, two consecutive A's. In case if you give the string AB, what happens here? In the above machine, it will not halt. It will never halt on AB. And TM accepts A star. AB, is it belongs to A star? No, right? So it rejects. That means TM either halts at non-final or never halts on AB. It's going to happen. The another one, first one is halting behavior, second one is acceptance behavior, third one is TM enumerates A star. Enumerates A star. What happens at this point? It will produce, it will enumerate like epsilon A, double A. It will put on the tape somehow. This is how it's going to perform the language at different ways. You can halt on a given requirement, or you can accept given set of strings, or you enumerate given set of strings. This is how you compare halting, acceptance, and enumeration. You can have the difference between all these three. Okay. Constructing the Turing machine for any language like regular, finite, DCFL, CFL, CSL, recursive, all of them are called as recursively enumerable, right? If you want to construct a Turing machine for any of these languages, first you should know how you write transitions in Turing machine. Before explaining the first language, which is A power n, B power n, first how you design, or how do you write, or how do you construct a Turing machine with the help of transition. Okay, I'll try to help. Suppose you have a Turing machine that is, let me take DTM transition. How did you form a domain and codomain for the transition function, which is Q cross? Either you can call gamma or tau, that depends on which symbol you take. So I'm taking the tau as tape alphabet, which is Q cross tau cross left or right, that's the direction. Okay, now think about this tape alphabet. You know, there are many things that you need to understand with an example. Let me write Q naught. I'm doing something here. I'm maybe in the same state, but let me write something I'm going to write. What is the meaning of this transition? You know, you are in Q naught state. You are moving to the same state. That means it's a self loop. What you are reading is A. You are reading A, but you are writing with X. This is the first important point. What you read and what you write with, that is, I'm reading A, replacing with X. In the tape, what happening is, you are reading A right now. You are in Q naught. Again, you are going to the same state, but you are replacing with X and taking one step right. Take one step, that's one symbol right. That is going to A comma X comma R. You can use the three parameters in a transition. That's A comma X comma R, means you are reading A, replacing with X and moving right direction. So the first point, how you write a symbol. How do you write a symbol in Turing machine? Why do you write a symbol basically? Normally you don't do in finite automata and PDA, right? You don't write with any other symbol. But in Turing machine, you are writing with some other symbol, means you're trying to remember it. Like in PDA, if you want to remember, you were pushing onto the stack. You were pushing onto the stack. But here, there is no such stack. There is no such stack or such additional memory. On the tape, you can read or write. So I have a very powerful feature, which is nothing but a write feature. If I'm writing with some other symbol, means I'm able to remember it. If I don't write, that means I don't want to remember it. I just want to read it. I will take an action. When you are writing it, when I come back, that means I know some other symbol is there. That means I somehow remembered that A was replaced with X and I'm doing something else there. Okay, so this is how the write feature can be applied on the Turing machine configuration. Now let's move to the read. I don't want to write. I just want to read like a finite automata and push down automata, but I don't want to push something onto the stack. That too. I don't have a stack here. So how do you read? How do you read the symbol without writing it? For that, if you have A, you have to replace with A only. Almost you do the same way, like delta Q naught A is equal to, let me go to some other state, Q1, I'll keep A and I'm going right. It means from Q naught, we are moving to Q1. When we read A and we are replacing with A, means we did not write with any other new symbol. It means A was there while reading. After reading also A only present. That means this A will not be replaced with any other symbol. It's replaced with the same symbol, means nothing, no write happened to that A. No other symbol is taken place at A. This is called as read feature. You can read the symbol without writing. It means read and write with the same symbol. Fine. In case you want to move a left direction, then this write you just replace with L. If I want to move left direction here, of course this transition, this is not a write. This is going from one state to other state. Okay, don't assume this transition is right to left or left to right. This is never be right to left, left to right. This is only the parameter which we'll talk about. Are you moving left or right while reading the input symbol? If you want to go left, then you have to replace here left. Okay, so remember, here we are moving to the right. We are moving to the right. That's why I have taken the R in the third parameter, right? In the third parameter, that's the third parameter. Now we'll move to construction of the Turing machine. So now I can help you how to construct the Turing machine. The first example is a power n b power n. Already you know how to construct the PDA or DPDA because it is a DCFL, deterministic context free language. You can definitely design DPDA, but you can also design PDA. You can now design a Turing machine. Suppose you might be designing halting Turing machine. In fact, you are designing LBA, but I'm just calling Turing machine, but internally there are so many meanings for the Turing machine. Might be you are designing linear bound automata, but you are not aware what is the difference between linear bound automata and Turing machine. So we will just call that is the Turing machine, but actually it is linear bound automata because you never cross the tape length. What is given to you, you are using the same bond without taking exponentials tape length. What is this a power n b power n? How you can understand the string with the help of Turing machine? Okay, let's say this is your string. You have the blanks. Let's say it's a two-way infinite tape. Now you are starting here. Your input is placed right side only. Don't assume left side. Okay. So I have to move to the right if I want to read whole input. Now here, how I do? Remember 4 A's and 4 B's. If you have the stack, what you did, you pushed all the A's and every B you popped 1 A because you can only scan once there. But in Turing machine, you can scan any number of times. There is no limit how many times you scan from left to right or right to left because your head has the power that you can move either direction and any number of times. Any number of times means now very simple logic, right? No, I want to scan many times. Every time I scan 1A, 1B, I will cancel or I will change the symbols so that if I scan 4 times forward and backward, then each time 1A, 1B got cancelled somehow. So 4 A's, 4 B's are there. So every time I scan 1A, 1B, I'll change. Every time I scan 1A, 1B, I'll change. I ask, sir, how I go forward 4 times? Because you can come backward. How? I'll go forward somehow like this, then I'll take backward. Again I'll go forward, I'll take backward. I'll go forward, I'll go backward, and so on. Every time 1A, 1B cancel here. Somehow these are cancelled. Here 1A, 1B. Each time I do 1A, 1B cancel. Then at the end, when I come back and if I am trying from the 5th scan, you will never see A comma B. That means your string is valid. How I did is, I'm trying to ensure that equal number of A's and B's by doing many scans. Whereas in PDA, this was answered very easily. Like just do one scan, take the help of stack, but that was a push down automata. It has less power in terms of the language's acceptance. Right, the PDAs that you can design compared to Turing machines are less. Right, you have even though infinite context free languages, but they are having the smaller class that compared to REL's class. Now let's plan this and try to design what Turing machine. I hope the idea is very clear. I am going to scan many number of times, but for each scan, I'll remember or I'll replace the A and B somehow. Like the first time A I'll replace with X, B replace with let's say Y. Then second time this A I replace with X and this B I'll replace with Y. So first scan, second scan, and third scan this A I'll replace with X and this B I'll replace with Y. In the fourth scan, this A I will replace with X and this B I'll replace with Y. When I'm trying to do the 5th scan, here I don't have A, I see the Y. That means all the A's are taken care. Now this Y's, after this Y's there should be no B or A. That means after this Y's there should be blank rather than small a or small b. This is how you think about the equal number of A's and B's when A's are followed by B's. Okay, let me design the machine, but remember the logic what we did. In every scan 1A 1B we written with some other symbols. At the end of the 4 scans, that's the fifth, in the 5th scan we did not see A here, because after this 4th A, 5th A must be here, but there is no A, means there is a Y. If there is a Y, then ensure that only Y's are there, after that blank is there. It means the number of A's, number of B's are they are going to compare and they are exactly same. Okay, now let's start designing a machine. The approach is same again. One, two, three, 4. What is your first initiation? The Q0 is initial state that will take care of replacing A with X, but it will not be in the same state, it will go to Q1. So let me explain that to the states now. Now what is the Q0 job here? Replacing A with X, but somebody has to give the control to Q0 whenever it want to replace A with X. Fine, the Q0 job is replacing A with X, then give to Q1. What is the Q1 job? Is to find the first B. To find the first B. It's trying to find the first B. But when it is occurred, it will replace B with Y. It will only replace B with Y. Then immediately, so far you are moving right direction. But there is no use of moving right, as you don't have a other symbol to compare. Like if you have A power n, B power n, C power n, then you could have moved right direction now. But here you will move left direction. You will take left, and you will give to Q2. What is the Q2 job? Q2 job is to find the first A. Not this A. This A is no more, right? Find the first A in the reverse direction. So how long you find? You need to move, right? Here you are pointing this time here, and you move. Keep on moving left. Keep on moving left. But how do I know this is the first A? Because you have X. After this X, if there are so many X, after the last X, when you are coming in the reverse direction, after the first X, you will see the A if there is anything. So here it will check, okay, Q2 is seeing X, then immediately it will give to Q0. Immediately it will give to Q0. And what is the Q0 job? It has to see A. If there is no A, then definitely you will see this Y, because when all these 4 A's are replaced with X, then definitely the Q0 will point to this. So anyhow, now the same approach, keep on repeating. The one scan I have shown you, the remaining scans you do the same way. From here onward, same. This A will replace with X and gives to Q1. And what is the job of Q1? Taking right. But how long? When it says the first B, this one, that means it has to skip the Y also. It has to skip the Y also. In the first scan, there is no X comma Y, because you are writing them in the first scan only. That's why you don't see them right before writing. But in the second scan, the Q1 is able to see the Y. Q1 is able to see the Y. That's why the second scan is very important. What are the symbols? New symbols are going to appear during transitions. Now Q1 on B, then it has to replace with Y, then give to Q2. What is the Q2 job? Q2 job is to find where is the first A, this one. And now onwards, same. It will AND over 2. How it finds this A? It can't directly. So it goes to first to the X. Then it will give to Q0. So now Q0 will point to this third A. It's keep on repeating. At the end, what happens? If the Q0 is not able to see A, that means it will see the Y. At that time, then go to the new state, let's say Q3. The Q3 job is to identify these are only Y's. Then blank should come if you are keeping, if you are moving right direction. When the blank comes after skipping all the Y's, then that's a valid string. I hope you got a logic. You need to design the machine. See how much time you spend just design one Turing machine. That's why this kind of questions not happen and may not happen in the objective type gate exam. Okay, in case if the gate exam converted to the descriptive, then they may ask design the Turing machine. Right now we do not have much time, as you have only 3 minutes. In the 3 minutes, of course, understanding the language only sometimes takes time. Then when will you design the machine, right? Now let me design the machine with the help of these transitions. Q0. What is the Q0 job? Q0 job is to replace A with X. How do you do that? Replacing A with X and moving to Q1. Replacing A with X, moving to the right. I hope you have a clarity. I already explained it. Q0 to Q1 you are moving. Q0 to Q1. So this transition is going to replace A with X every time. But somebody should give the control to Q0 whenever the A is in, whenever the next symbol is A. Q1. What is Q1? Q1 has to skip all the symbols. But who are going to come from Q1? A, and in the future it may be Y, because you see that Q1 when it is skipping A, and that is a Y, so Y may appear, but X never comes. Remember, because we replace A with X, will take right turn, so Q1 will not see that X. Q1 is going to read a lot of the symbols like A. Don't override with any other symbol. Keep the same but move right. Not only A, it could be possible that Y also may come. After Y you will see the B, right? So the Y also we read and we take the right. Why do we want to take the right always? Because I want to find who is the next B. I want to find who is the next B. You can see now the Q0 is here. After replacing this A with X, then Q1 will begin from here. Q1, skip A, skip Y, and then B comes. When the B comes, you replace with Y, but take left right now. So here we take left, right? Here we take left. When we found a B with the help of Q1, then immediately it replaces with Y, takes left, and goes to Q2. Q2 job is to do the reverse scan. Blindly it does reverse scan. So while doing the reverse scan, you can see that the Q2 may see the Y or may see the A and may see the first X. But before the first X, all the Y's and A's, need to be skipped. Y comes, then skip and go left, read, go left. And if A comes, read, go left, because you need to target X. When you see the X, Q2 sees the X. When it sees the X, take right turn immediately, but don't change that X. Take right turn immediately. Then you will come to, let's say, Q0. So this X, right? So no need to create the another state. You already have it, right? So I can go there. When the first X comes in the reverse direction, then immediately give to Q0. But take right turn. When you see the X, take right turn and give to Q0. This keep on happening. When you keep on executing this path, what happens? Every A you replace with X and every B you replace with Y. That means 1A, 1B is going to be cancelled in the counting. Now, when you keep on doing it, at certain point of time, the Q0 sees this Y because there is no A. The Q2 assumes when it sees the X, let's say this is the first X, when it sees the first X in the reverse direction, it immediately gives the next symbol, but next symbol is not A, it is Y, because all the A's are already counted properly. Now when Q2 sees, not Q2, right? Sorry. Who is going to see? When Q0 sees, when this Q0, instead of A, if it sees Y, then take just right, give to Q3. What is this very special case? Very special case is when you have the situation like, let me explain here. x, 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 y, 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 y. When you have the situation and Q2 was taking the left scan, when Q2 sees x, it immediately gives to Q0. Q0, when it sees the y, what is the Q0 job? Replacing A with x. But if it sees the y, it means all the A's are taken care. So it should be same for B's. All the B's should be replaced with Y's. So Q3, to ensure that only B's are left and all the B's should be replaced with Y. Otherwise it's not the valid string. Only Y's are there. Take right. If you keep on doing this, take right from Q3, right? It goes to Q3 and keep right. When it sees the blank, Q3, when it sees the blank, that means our string is valid. If Q3 is not able to see the blank, then it's not the valid string. So whenever Q3 sees blank, then do whatever blank you replace with the blank, or do go left or right, but go to final. So this 2 dashes is your choice. Blank you replace with any symbol will not impact for this problem. Okay. Now check for this language epsilon. Is it accepted? If it is epsilon, then Q0 directly sees the blank, right? Q0 will directly sees the blank. Is that covered? A is covered, Y is covered. But when Q0 sees the blank, you go to final state. Take replace with any symbol and take right or left, doesn't matter. That is a very special symbol. Apart from that, 1A, 1B. 1A and 1B replace with X and Y. When you take left, after A you will see Y, so you will take this path, and after Y you will see the blank, then go to final. If there are many Y's, then skip, otherwise go to final. It might happen epsilon when you have no symbol here, so the head directly points to the blank. Then when it is true, Q0 when it sees the blank, then go to final. This motion is for accepting the language which has A's followed by B's and equal number of A's and B's. Okay. Here don't worry about how many states you have, but this motion should accept all the valid strings of this language. It should never accept the invalid strings. That's how we designed. Okay. Let's move to the next question, that is almost same, only the change is we have added extra symbol C. We have checked A's and B's are equal, but now one step ahead you have to do C's are equal. What you did, every A you replace with X and every B replace with Y, and you have taken the left direction after replacing B with Y. But now after replacing B with Y, now check for the next symbol, that is C in the right direction. After replacing C with some other symbol, then take left. Every time you are going to compare A, B, C. As A replaced with X, B replaced with Y, C replaced with G. And then take left. Again same process, find the first X in the left direction. So whoever is turning left and moving left direction, that state has to ensure there is a first X, there you should hand over to Q0. Right after X, whoever the symbol is there. Okay, then before going to this example, let me explain. Sometime you may require to construct the table, or you might require to write the transitions. Let me help you with the previous example. We have drawn, right, A power n, B power n. So Q0, what it was doing? Okay, there is no self loop. Initial state. Q0, whenever A comes, it will replace with X and move right. It goes to Q1. When you have the transitions like this, there are so many transitions, obviously. I'm not going to write a transition table for all, but I'll help you for this, how you treat in the table. Okay, from Q0, which symbol you are reading? A. This is very important. Q0 A, but which state you are going? Q1. and now x comma r. This is how you represent in the table, but in the diagram it's something different. Q0 to Q1, this a comes here while you are drawing the diagram. This is a pictorial representation and this is table representation. If you really want to write as transitions, you will put a number for this like 1 delta of Q0 comma a. This is a delta table, right? A is equal to Q1 x r. This is how you require, right? If you want to write all the transitions in a sequence, then put this way. And if you want to draw a table, Q0, this must be input symbol, and this is what you are writing and which direction, what is the next state. And these two are not exactly look same, but the meaning is same. Here these three parameters, here three parameters are different, but these three parameters are reading, writing and direction. These three parameters are next state, writing symbol followed by direction. Okay, so understand these two are exactly same what you have, table and transition function, or the mapping. Let's move to the next example. Now, are you ready to draw the diagram? Obviously, before drawing the transition Turing machine diagram, first work out, are you going to take 5 states or 6 states? So have a proper logic what you are going to do. So I'm going to take a simple example to understand what's happening here. Okay, 5 A's, 5 B's followed by 5 C's. There is a blank, and so I'm going to work on this. Okay, Q0 job is to replace A with X, and somehow it will go to Q1. A Q1 job is to find the B and replace with Y, and now Q2 comes into the picture. Now Q2 is going to take right direction to find the first C and replace Z, and Q2 gives to Q3. And what is the Q3 job now? Previously Q2 was taking the reverse direction, but now Q3 will take. The Q3 job is to find, where is the first X? Here is the first X. So here, when it sees the first X in the reverse direction, it will give to Q0. Now again, Q0 sees first time this A, so next time it will replace with X, and Q1 will replace with B, Q2 will replace C with Z, and then Q3 comes in reverse direction. At the end of this scanning, you will see something like this: blank, X, X, 5X, 5Y, 5Z, blank. When Q2 is written the C with Z, it was actually C written with Z, it will give to Q3. What is the Q3 job? It's take left direction till you see the first X. Here you will see the first X, and it will immediately give to Q0. But Q0, when it sees a Y, Q0 knows that there is no more A left. This is an indication of accepting a string, but don't accept immediately. Ensure that there is no symbol left from B and C, and there is no A after this Y and Z or in between anywhere. So now Q0 will skip the Y and Z. Of course, after Y only Z comes, we know that because we have only written it. Just put a self loop, Y's and Z's, just skip them. If you get a blank, go to final. So when Q0 sees a Y, it will give to, let's say, Q4. It will give to Q4. And Q4 job is to skip everyone to reach the blank. If it reaches the blank, then go to final. Okay, let's start doing it, but you should know exactly how the Q1 reaches the first B. It's not that easy, that you have seen here, because if Q1 want to reach the first B, it has to skip the A's and also Y's in case if they are written by the previous positions. So A's and Y's need to skip by Q1 so that it can reach the B. And what is the Q2 job? Q2 job will replace, Q2 job is to find the C. But to find the C, all the B and then Z has to skip. then only it will reach the C, because before C Z may come. Again, now what is the job of Q3? Q3, when you are trying to take the reverse scan, before C Z's may be there, before Z B may be there, before B Y's may be there, and before Y's A's might be there, after A's, that means before A's from this direction X. So first X, when you see, the Q3 will take right turn and give to Q0. This procedure is going to be covered in your diagram. Let's start without wasting the whole diagram picture, or all the required things are there here which are required in diagram. Okay, diagram needed little bit big. Let me draw. Very simple. Q0 state, Q0 state, and then Q1 state, and then you require Q2 state, and then you require Q3 state to do the reverse. And once you complete Q0, complete all the A's, you need a Q4, and Q4 will skip, and then you require final state. The final state requires fine. Initial state, every A you need to replace with X. And what else you needed? Q1 to Q2 somehow you will go when B comes, and when Q2 sees the C, it will replace with Z. And I'm just putting, I'll write the transitions later. I know the whole flow chart, so that's why I'm making these edges. And Q3 will give the control to the Q0 when it sees the X, and Q0 will give the control to Q4 when it sees the Y, and Q4 will give the control to final when it sees the blank. Because there are many self loops. Okay, let me draw that. Here you need a self loop. One self loop here. Here there is one more self loop. Here self loop means you have transitions there. Here also you have transitions. Okay, let me write what are those transitions. Can you understand one by one quickly? Okay, let me write the names also. Q0, Q1. Of course, if you do not have the complete picturization, drawing like this would be difficult. So do one by one at that point of time. If you don't have a clear idea, just do one by one the final state. Any Q5 state which I have taken up? No, right? Let me write the transitions now. What is the first transition that you are looking at? That is when Q0 sees the A, replace with X, take right direction. Okay, that's the first thing that you did it. Then what is the Q1 job? Q1 job is to skip A's and Y's. Why Y's? Because this Y's might be written by the first and second scan if you are at the third scan. So that's why we are trying to cover the Y also. But first time when you are scanning, Y is not there. That's fine. But second scan onwards, you need to skip the Y. So both should be taken care. A's, take right turn. What else? B's, you don't have. Y's, take right turn. But why did you go? Oh, sorry. That's at Q2, right? I should write copy paste. Sorry. I should copy paste. I thought this is a Q1. No. Here. A, right. What else? Y, right. At Q1. Still we did not go to Q2. Only we are at Q1. The Q1 job is to skip A and Y. If you want really the meaning, I'll also put that. So remember them. This is to replace A with X, right? Replace A with X. So you can write replace. A with X. This one skip means do nothing, but skip A, you know that will happen. This is just do nothing, just skip Y, means read A, read Y, that's it. Read A and read Y. What is here? When we go from Q1 to Q2, Q1 to Q2, when you see the B, you replace with Y. When you see the B, you replace with Y and take right. Similar to replace B with Y. Here, what is the job of Q2 here? What is the job of Q2? Q2, after replacing B with Y, Q1, after replacing B with Y, then it will give to immediately Q2, right? It will give the control to Q2. Q1 job, what is the Q1 job? Skip A and Y and find the B, replace with Y. So that's the Q1 job. Once the Q1 is over, then Q2 will come into picture. Now once it handovers to Q2, whenever the Q1 main important job is over, that is replacing B with Y is a main important job, right? Once it is over, once this job is over, replace B with Y. Once the job is done, you will the Q2 will come into picture. What is the Q2 job now? Q2 is going to find the C, but to find the C, it has to skip a lot of symbols. It has to skip the B's and Z's. So B, right. If you see the Z, Z, right. If it does B and Z, then it will see the C. After some time, it will see the C, then C will replace with Z and take left direction. Why? Because you have completed one scan. And when the one scan is over, you should take left turn. So I have taken it. Now Q3 is going to take the left turn. But what it is going to see Q3? When you are, let's say some random step, let's say third scan, when you replace C with G and Q3 will point here, Q3 can see all the Z, these are Z's, and B's and Y's, A's. So 5 different symbols it is going to see somehow. First, it might see this Z. So I need to write somewhere. Let me write here. Take left for this self loop, and then before them you will see the B. Before B, Y's. Before Y's, A's. But when it sees the fifth symbol, different symbol, X, then it will hand over to Q0. X, replace with X, but take right turn. There is one complete scan is over, one forward scan, and here onwards reverse scan begins, right? So one forward scan and one reverse scan, one scan completed. Just keep on repeating so that all the A's will replace with X, all the B's will replace with Y, all the C's will replace with Z. And Q3 does its job. Whenever it sees the X, it will give to Q0. But now Q0, what it sees, there is no A left. When there is no A left, what Q0 will see? Q0 will see whoever it is standing here, Y. So what is that Y? Here Y, when it sees, replace with Y but take right turn, because now only one scan can decide the final acceptance. Now Q4 job is to skip all the Y's and to skip all the Z's. If you do that properly, if all the Y's and Z's you skip it, you should reach the blank. When you reach the blank, doesn't matter what you replace and which direction you go, because anyhow you are going to halt in final. Is it going to accept every string? Look at that, except epsilon. Suppose there is no symbol ABC here, then directly blank is going to appear from Q0. In case if you see from Q0 blank, what do? You will go to final directly. You will go to final. So from Q0, if you see the blank, you will go to final. That's on blank. To accept epsilon. I hope with this you got a clarity how big the Turing machine is, why we don't expect in GATE exam such kind of questions. You should know how to design, but in the exam you should just understand, do you have a Turing machine? That's it. Not what Turing, you don't need what kind of Turing machine that you are going to think. think about, but just have a logic, and based on the logic, if you can build the Turing machine, you can say the language is real. Okay, now third, construct TM for one's complement of binary. This third one, but you may have a thought that, sir, these machines are similar, not these machines, previous machines, like these machines are almost the similar to the finite automata, except that what do you write, which direction. If I delete these two parameters, the machine looks like a finite automata, right? Now, sir, I have a, let's say, a star, L is equal A star. Can you construct Turing machine with the help of the finite automata? L is equal A star, the finite automata, right? Is this finite automata, whether it is DF or NF, it doesn't matter. It's a finite automata. Do you have any algorithm to convert this into Turing machine? Can you construct Turing machine? Any finite automata, can you construct Turing machine? Yes, you have an algorithm to convert from finite automata to Turing machine. But how? Copy paste old machine, but don't keep any final. Understood? Copy paste old machine, but don't copy final, because final we always take care with the blank. Now, what is the job here? This A is there. As you know, there is no write feature in the finite automata. So what we add additionally, A comma, the same symbol you write and you take always write. That's all. You do it. A comma R is the transition that you take. Now, after doing for every transition, if B is there, then for B also you write B comma R. Every symbol that you see in this machine, just replace the same symbol comma R, put with the 3 parameters, keep as a one transition. At the end, this is the final. From the finals, if there are 3 finals, from those finals, just add a new transition, keep a blank, take right or left, doesn't matter, and go to final. So this is a new final. And any finite automata you can convert to the Turing machine just by adding the 2 extra parameters for every transition. Let me add one more. Suppose I have a different machine. Let me take a little bit bigger. Suppose I have this machine. Some machine you have here. So now, how you construct the Turing machine for this? Very simple. Copy paste the whole machine, as I said. Copy paste. We are always good at, right? A, B. Oh, this A comma B is the right. Just better to write A one transition, B another transition. Of course, there are 2 transitions, but for understanding easily, this A comma B might mix up with the TM transitions. You will confuse. So better to write separately. Now what I did, for every position or every symbol, just write with the same symbol and take right. Here B is there, write with the same symbol and take right. That you are only reading. And now say that you are writing with the same symbol and take right. That's it. Now it's not at over. There's no final, right? New transition you have to take. Who are the finals here? B. From this B, just take a new transition, put a blank. Oh, this B, both are different, okay? Blank, right. That's it. This is how you design a Turing machine. If there are 3 finals, from those 3 finals, just take this transition blank, right, go to final. Okay. Any finite automata you can construct or you can convert to a Turing machine, just small changes in the machine. Okay. Some points can be asked in the exam. Look at this. Every transition in this Turing machine, always you have the right move, and it is only reading. You don't have the right feature at all. You are reading with you are writing with the same symbol. So 2 points. You are writing with the same symbol. You are always taking right direction. It means whatever this TM, that is accepting regular language only. When will it accept regular language? If you are writing with the same symbol and you are moving only right direction, then the language accepted by that Turing machine is regular. Such points are many, and understand there are a lot of theoretical points behind this Turing machine construction. We need them. Okay, I don't know whether you construct the Turing machine easily or not, but at the end of the day, the concepts that are important for the exam which should be answered. Okay, construct the Turing machine for the ones complement of binary. Understand, this Turing machine is different from the acceptance behavior. In the acceptance you require a final state, so that every valid string it will alternate final. But here there is no such thing as valid. You give me any binary, you will be having ones complement. So if I give let's say 1101 to my Turing machine, it has to replace with somehow the 1 with 0, 1 with 0, 0 with 1, and 1 with 0. That should be output, right? The ones complementary. There is no valid string, invalid string concept here. Anyhow, any string which is over 0, 1 is a valid. There is no such invalid string in the 0 plus 1 whole star. Every string except epsilon. Epsilon is a very special input here, right? Epsilon you can ignore if you want. All the strings, all the binary strings, you have the corresponding ones complement. Here alternating behavior is considered. Whenever its job is over, whenever it replaces with zeros with ones, ones with zeros, it is going to halt. The tape halts after some time, but you will see on the tape the proper output. In the input tape, in the tape you will see 1101, 1101, right? This is your input, right? It's going to do something. It doesn't matter where it starts, how it starts, but always the head is here. Now you decide you want to start scanning from right, then move right till the end and start scanning from there. Okay, you want to find something from the right. But anyhow, I want to do only one scan. The one replaced with 0, 0. I'm taking right turn. 0 replaced with 1, 1 replaced with 0. And when I see the blank, I'm going to halt. That's it. That is a behavior. I no need to take many states for, especially this example. Other example, you may need more states. But this example is one state for reading all the symbols of the string, then halt at the end. Only two states, Q naught and halt state. So how you design Q naught? It's going to replace 0 with 1, take right, and replace 1 with 0, take right. And whenever you see the blank, it's very important, keep the blank, but move right or left, it doesn't matter. So I'll just put the right, but you can leave it. You can also put left, doesn't matter. Now I'm going to halt. See, I did not mention any final state here. Just I'm mentioning halt. Means now the machine is going to halt. After this, no more job left, because my input is replaced with the proper output here. Every binary input, there is a corresponding ones complementary output. That I'm going to do ones complement of the given binary. Okay. You can also try constructing the table for the same problem. If you have any other approaches, yes, there are thousand approaches to design the machine. Same logic you can follow, like I can go to the till end, and from there I can replace 1 with 0, 0 with 1. Still you will do the same job. Finally you will see the ones complement of binary. In the exam, to confuse you, okay, I'll just tell you how the exam they are going to make a question for you. Okay, I'll just make a machine for you, and look at here. 0, 0, take right. 1, 1, take right. When you see the blank, replace with blank, but take left. Here, every 0 replace with 1, take left. Every 1 replace with 0, take left. When you see the blank, replace with blank, take left and halt. See what I did. They might give a machine, and you need to understand what is the functionality or what is the behavior of this Turing machine. If I give the input 0, 1, 1, let's say blanks are here. What's happening? Take an example to understand. because in the exam you will be having 4 options. This example will help you. Is it doing 1's complement, is it doing 2's complement, or is it giving the same string as it is? It all depends on what do you take. Take the input little bit lengthy, lengthy means 3 to 4 bits, then work on with this Turing machine, you may get an answer. Let me help you that. Let me help you how to do that. Here Q0, this is input, right? What I am taking input is 0 1 1. I'm going to find what is the output. Then you may get some conclusion from this given input. Now from Q0, when it sees the 0, what it does, it's just skipping, right? 0 or 1, go right, go right. I'm going right, go right. When it sees the blank, it will take left. It will take left. Okay, so it will take left and gives to Q1. What is the Q1 job? Q1 job is, now see, 0 replaces 1, 1 replaces 0, but take left, take left. So Q1 here, this one replace with 0, take left. This one replace with 0 because self loop. 0 replace with 1, and here when Q1 sees the blank, when Q1 sees the blank, halt, then immediately it goes to halt. What has happened? What is the output? 1 0 0. Tell me 1 0 0 is what? 1's complement of binary only. Have you seen? What I was explained was 1's complement of binary, and what I have given is also 1's complement of binary. This is why, in the exam, if they are going to ask, what you do is to understand as per your logic, but in the exam, even though logic is nearby yours, but machine is not designed the same way. You are directly started doing 1's complement 0 with 1, 1 with 0, but they may not do it. They just want to do the time pass, go to the end of the string, and they start doing 1's complement from the end, so which is going to take time. They are trying to waste your time in understanding the functionality. So that is why it's very important what machine you have designed. Functionality wise it's same, but previous one will take less time to do the 1's complement, this one will take more time to do the 1's complement, except that the job is same. Okay, this is another way, rather than going for the acceptance or designing the machine, halting properties, we have many ways to design the machine. First type, we have understood how to accept the strings using TM, and second, halting machines. Whenever the job is done, you do the halt. You do the halt. Now, I hope, can you do this 2's complement of binary on your own? I'm giving you homework. What you have to do? 2's complement of binary. You can do many ways. Better to scan that in reverse direction. If you really want to see, example, let me write 0 0 1 0 0. This is my number. If I'm going to do the 1's complement, what happens here? 1 1 0 1 1. Then add 1 to this. What happens? 0, again carry 0 and 1 1 1. This is going to be our 2's complement, right? 1's complement plus 1. It's a 1's complement plus 1. You got 2's complement. But can you do this directly from the input? Yes, it can be done another way. How do you do that? 0 0 1 0 0. Now see, till you see the first one, keep same. But after that, just do the 1's complement. So till the first one, you keep the same, including that first one, but after the first one, whatever you see, just do the 1's complement. I told homework, but let me do in my way, but if you have any other way, please try that. So now, what is Q0 job? Q0 job is to find the last one, this 0, because there I want to scan. What do? You can't do directly, 0, you can't go there directly. You skip everything, 0 0 right, 1 1 right. With this, you will reach the blank. What do you reach? You will reach the blank. That blank will help you to move to the another state. Blank, replace with blank, take left. then here onwards your logic begins. Q1, what is the Q1 job? To find the first one. To find the first one, any number of zeros, take left, but when you see the first one, take left only, but here give to Q2, give to Q2. Right here Q1 is there, and whenever Q1 sees the 1, it will keep the same but go to Q2. Now Q2 job is to do the 1's complement, 0 replace 1, 1 replace with 0. Here the Q2 is going to do 0 replace with 1 left, 1 replace with 0 left, and that happens till the another blank comes here. When the blank comes, go to final and move left or right, then F, go to final. Epsilon, that you take care of it, as epsilon is not a binary number, but in case if you want to produce 0 something like that, just take care of it. But, if the now given number is binary, definitely it is going to perform the 2's complement. Going to perform 2's complement. Q1 is the crucial here. It's going to find the first one in the reverse direction. To find in the reverse direction, first Q0 will help us to reach end, and from there the Q1 will take the control, and all the zeros will be skipped in the reverse direction. But when the first one comes, it will hand over to Q2. Q2 job is to replace every 0 with 1, 1 with 0. Whenever it sees the blank, go to final. So this is the whole picturization of 2's complement of binary. In case if you have any idea different than this, like 1's complement plus 1, yes, you can also do the 1's complement, add 1 extra. If you want to add 1 extra, what should be the logic? You just think about it, and if it works, you just design a machine. Let us know. I'll help you if you are coming with the different answers. Oh, this one, see the behavior. Somebody want does not halt. Okay, there is also halting kind case, right? Does not halt for a plus b whole plus. How do you design if you want to halt on epsilon? Does not halt for a plus b whole plus means what? A plus b whole plus, it will not halt, means it will never halt. Not going to halt. But epsilon, it should halt. Other than those strings, what? Halts. Now whenever you start designing, from initial state you see the blank, go to final. Sorry, not final, there is no final concept, that's why it's just halting nature. Whenever you see epsilon from Q0, say halt. But other than that, show me that you will never halt. Show me that you will never halt. Okay, many ways to design, not one way, two way, many ways to design. So I'll try to help my way, because as I told, there are many logics. When there are many logics, your logic may not match with my logic. Okay, that's one of the important point. Okay, let's begin. What is my logic? As you know, when you are writing a program for any problem, that solution might take much time, right? The problem complexity might be complexity of your algorithm maybe big, so you need to reduce the complexity sometimes. Okay, similar way, I might be constructing the bigger machine which might take time. You may think better machines. Now what I am going to do here, if directly blank is happening from the initial state, I'll alt. Now how I do for various strings, let's say I am taking one string, what is my approach? That never halts. Okay, that never halts. So I'm going to do something. There are many ways, believe me, there are many ways. See, from Q0, A comes, skip Q0, B comes, skip A comes, skip blank comes, skip blank, skip. Just definitely keep on going it, but Q0 on blank is very difficult, right? As you know, epsilon also is going to happen from Q0 only blank, so you can't say that this situation. When Q0 sees the blank, then this is matching with the epsilon. That is the reason when Q0 sees A or B, just jump to other state, that state will take care of it. So when Q0 sees A or small b, then it will give to Q1 whatever it sees, moving right, never halts. It's a one case. Okay, Q1 never sees, never think about any symbol. Keep on moving, either A or B or blank, moving right. Or from Q1, you can also move left. You can also move left. No need to move right. There is another way. So one way is doing this way. But it's very simple, right? There is another way. Q1 only can move left. It can move left. Whether it is blank or A or B, doesn't matter. It will keep moving left. Third one, already you have come here, right? Just take one more left and then one more right. Left, right, left, right, left, right. That means here only you are forming that kind of infinite loop that you will never halt. There are many ways to design this problem. Okay, I'm just going for the simple one, but there are other situations. What is other situation? See this, you try to think about here. Q0, when it sees A, it gives to Q1. When Q1, whenever it sees anything, it will give to Q0. Q0, whether it sees A or B, it will give to Q1. Here only you will never halt, right? This is a very standard and very popular for competitive exam if they want to ask. Now I'm going to think about this motion. From Q0, if you see the blank, keep the blank, take right or left, doesn't matter, I'm going to halt. As I want to design a motion that never halts for A plus B whole plus. Now onwards, if A or B comes, first job is take right. Whether A comes or B comes, you take right turn. Now Q1 should ensure that it never halts. For that, A or B or blank, keep moving right. Just keep moving right. You can put a self loop. Really you want it, take right. Blank, sorry, B, take right. Blank, take right. Is there any way to halt it? No way. You are not coming back and you are not saying anytime halt, right? This is one way. I told another way, this one. Whether A or B comes, take right. And this one, whether A or B comes, take left. Here only you form what? Loop. Here the blank may also come. Let me design another one. What is another one? From Q0, if blank comes, halt. Either A or B comes, take right. A or B comes, take right. So one symbol only. Here from Q1, you may have a symbol, you may not. Even blank also may come after A or B, right? First symbol, after first symbol, if you don't have anything, blank may come. So Q1 responsibility is just take left turn. Whether blank comes or A comes or B comes, just take left. What happens here? These two will keep on here only, these two symbols only keep on repeating infinitely. Q0 says that go right, Q1 says go left. See, here only they are going to loop forever. If the string is not epsilon, then definitely it's going to not halt for any string in A plus B whole plus. Single A you take, A right, it will go to the next symbol blank. Q1, when it sees the blank, it will take left. Then again Q0 will see A, it says that go right. Q1 takes a left, Q0 takes right. It forms an infinite loop. So this is a very fantastic problem, and if you want it, it's a 3-star. If you can understand what I'm explaining, that's more than sufficient for the GATE exam in terms of construction. Really don't go for bigger problems like how to draw a Turing machine for prime logic, exponential 2 power n logic, a factorial logic. These things for the semester, these things for master level assignment questions. Right now at this stage you should know what problems you have a Turing machine, what not. That can be sufficient for the exam point of view. Fine. With this we got to know how to construct the Turing machine. Now I'll help you what we are doing with these two languages, recursive versus REL. Recursive versus REL. Now let me help you about these two languages. Turing machine is only going to help us to understand the definition of recursive language as well as RE language. Even though we say that for the recursive language we need halting Turing machine, but halting Turing machine is actually a Turing machine that always halts. So here we have two definitions or two languages, right? Recursive and RE. What is this recursive language? This recursive language is nothing but the TM halts always while accepting some language L, then that L is called as recursive language. Here RE language, what is it? For this, TM halts on every valid string of particular language L, then that L is called as RE language. We already seen this definition here, and this one is also we have seen what is the definition of halting Turing machine. TM halts always for every string, whether it is there in the language or not doesn't matter, for every string in the world. Okay, look at the difference. That's for every valid string. These are for every string, whether it is valid or invalid does not matter. The machine always halts. That machine called as halting Turing machine. This definition only we call halting Turing machine. Another definition of this line, right? The meaning of this line is halting Turing. Now, what is another point? Enumeration point of view. This RE language also called as enumeration, right? Enumeratable language. When TM enumerates a language, that language is called as, or enumerate set of strings, that collection is called as enumerable language, also called as recursively enumerable language. So it's another definition with the help of enumeration. But which order that enumerates, don't care, it enumerates, that's all. But here it's going to be decided here if TM enumerates in lexicographical order, you may say dictionary order, lexicographical order, and such language is called as the recursive language. All the recursive languages, their strings can be enumerated in lexicographical order, whereas RE language may be enumerated in lexicographical order or maybe any other order. We don't care whether it is enumerable in lexicographical order or not. Fine. These are the very important definitions when it comes to the RE and recursive languages. If you want to find the relation between these two, every recursive language is RE language. Every recursive language is RE language, but RE, either recursive or not recursive, it could stand anywhere. Okay, let's start with another topic, which is the closure properties of recursive languages. The very important operation that I'm going to discuss, but if you want to go beyond this, you learn on yourself. Okay, let me start with the basic operations like union, intersection. What are closed for these recursive languages? Intersection. 3. Complement. 4. Concatenation. 5th. Difference. 6. Subset. 7. Substitution. 8. Homomorphism. Very important things which might help you for the exam. Remaining, they told you just focus on them. Epsilon free homomorphism. No proofs here, no examples too. Inverse homomorphism. Last, finally. Hardly, this set I have seen in the exam. The first 3 operations only asked so far in the exam. Is if they are going to ask any other closure properties of recursive languages, they might stand till 10. But you should be ready for many closure properties. That is my intention. Here, what are the properties closed for recursive languages? Here, union of 2 recursive languages is another recursive language. So it is closed. I'm going to put the tick mark. When I put the tick mark, assume it is a closed. Okay, right somewhere here. When I put the tick mark, it means closed. Class is not closed. Fine. Intersection of 2 recursive languages, another recursive language. Complement of a recursive is again recursive. Very, very important operation. The first 3, you don't have a doubt at all, right? All the 3 are closed for recursive languages. Fourth, concatenation of 2 recursive. Difference is L1 minus L2, L1 intersection L2 complement. That complement already closed, intersection already closed. Oh, difference. Subset is not closed for any domain that you have studied so far, regular, dcfl, cfl, right? Subset of recursive need not be recursive. That's a very important point. Like subset of regular need not be regular. Substitution not closed. Homomorphism not closed. Because of that, this epsilon free homomorphism explained that's going to be closed. If you are going to substitute other than the epsilon, if you are always substituting with non-empty string, then this homomorphism is going to be closed. That's why we call epsilon free homomorphism. Inverse homomorphism is closed for regulars, dcfl, cfl, csl, recursive, rel, all. So these 2 points are very simple, 6 and 10. 6 is not closed for many domains that we have studied, and 10 is closed for many domains from regular onwards. Okay, and you can see how many are not closed here. The subset, obviously, substitution, homomorphism. You can remember these 3 important operations which are not closed for recursive languages. Remaining all are closed here. Union, intersection, complement, concatenation, difference, epsilon free homomorphism, inverse homomorphism are closed for recursive language. I hope you can remember this. Not big list, but still, if you really want to see examples for each one, you have to work on. There are proofs for the first 3 in the books. You can follow that too if you want to learn why union is closed for recursive languages. Okay, very important one. Among them, complement is very important, much needed for us. Similarly, let me go for recursively enumerable languages. Here, let me see the same list: union, intersection. Think about which one is closed or not closed. If you have already studied, try to get the answers very quickly. Complement. 3, complement. 4th, concatenation. Difference, set difference. There are many other operations like clinic, closure, prefix, suffix. You can write on yourself and think about it. Get the answers for them too. Difference, subset. 7. Homomorphism. Epsilon free homomorphism. Inverse homomorphism. Union closed, intersection closed, but complement is not closed. So this is where you need to remember compared to recursive and RELs, the complement is not closed for RL. Then what happens complement of RL, we'll see soon. Okay, here I am not giving any example to do that, but we will see what is the complement of RL. Complement of recursive is recursive, but complement of RE, what is the right answer? Need not be RE is correct, but we have other answers too. And concatenation is closed. Difference, you can see there, L1 minus L2 is equal to L1 intersection L2 complement. The complement comes, that is why difference not. Subset anyhow no. Substitution yes. Homomorphism epsilon free, and all these are closed for RELs. So here we have three lists in this side. Complement, so difference, subset already we know that it is not closed for many domains that we have studied. Keep this point with you. And now onwards, if I ask union, closed for both the domains, recursive and RELs. Intersection is closed for both the domains. Complement, closed for recursive languages but not closed for RELs. Remember the points clearly. Okay, with this knowledge, let's answer some of the questions. Before that, before answering some of the questions, I want you to think about undecidability versus decidability of the languages. We have a lot of questions about the closure properties too. We'll discuss them too. So here we have two languages, right? Recursive and RE languages. How these two languages are used further? So let me explain them. The language, okay, let me explain with the name, that's a decidable, right? Here we are going to come up with a few important points. One, decidable word, which is also called as, remember synonym only it is, don't think that is something different. Decidable language or recursive language, there is no difference. Whenever somebody calling decidable means remember recursive. Recursive means, understand the definition, you have a Turing machine that always solves. Means you have a logic for both valid and invalid strings. This is how you should conclude. If I have a program that always solves, it means you have designed halting program. Okay. Second, there is a special language called as RE but not recursive. Three, not RE. 4, undecidable language. How these 5 words are really interesting. If you do not know the meaning of these 5, this topic really takes much time. First, have a clarity of this definition in language. So far we were studying only RE as well as recursive, but other 3 words are also there. They have the definitions too. The definitions you are going to follow now. First one, decidable language. How these languages came first? Let me explain that too. Okay. Now, these are actually called as decidable languages, also called as recursive. All recursive languages are here. Now, this upper box is, let's say, all languages are inside only. You will never go outside then. Now, what is this pink color box is? All RELs, all recursively enumerable languages, RELs. Now look at that clear cut. We have other classes here. Can you identify them? There is a class from here to here that you can't see directly. Don't assume this is just RE, wrong. It is RE but which is not recursive. So these are all RE but not recursives. There are REs, but not just REs which are not recursive. Okay, this pink box including recursive called as RELs, but outside the recursive inside RELs called as all RE, or every RE but not recursive is inside. Okay, there are so many RE but not recursive here. Okay, there is one more class that you may see here, which is from here to here. Can identify it. What is that means? Which is outside the recursive, which is outside the decidable, which is outside the decidable means outside decidable, undecidable, not decidable, very simple, which is undecidable languages. Simple name. Who is not decidable, that's definitely undecidable, right? They're all undecidable languages. There's something which is you need to know. Outside the pink color box, which is outside the RE, means which is not RE. These are all not RE languages, not RELs. Look at that. Okay, now you see all the points, right? These 5 definitions are here exactly, and that 5 definitions we are going to understand. Decidable means recursive. Every string you will halt, whether valid or invalid. That's the first point. Second, RE but not recursive means outside the recursive, inside RE. What is the meaning of this? Here, every valid string you will halt, but invalid string we don't know. We don't know means we'll definitely, this thing you can't say that. I have the logic for valid, the logic for invalid. You can't say that. Here you will say logic for valid, but invalid string you don't have a logic. That's why it came out completely. So now when you talk about RE, you can only say that I have a logic for valid, but really I don't know logic for invalid string. I don't know. That's the best word. Don't say I don't have. Okay, don't know. When you know it, it is recursive. When you don't have it, it is outside. When you have it, it is inside. When you don't have it, it's outside. But RE means you have a logic for valid. You have a logic for valid. When you have a logic for invalid, that is recursive. When you don't have a logic for invalid, that is outside the recursive. So that's why we are inside RE. There is a not RE language. Not RE means you don't have a logic for invalid, you don't have a logic for valid strings. You don't have a logic for valid string. So let me write a simple line to remember. The decidable means logic exists for valid and invalid. That's why you are able to halt all the time. You're able to halt all the time. RE but not recursive. So, okay, one more point. Every machine that accepts decidable, is it going to halt? Don't say that. Because I can design a Turing machine that only halts for valid strings of this decidable language. Okay, so be careful this point. Whenever you have the recursive language, you can or you may always design a Turing machine that always halts. But don't assume if this machine is accepting this decidable language doesn't mean that this is halting Turing machine. It may be just Turing machine, but definitely you have somewhere halting Turing machine. Okay, because logic exists for both valid and invalid. RE but not recursive means here logic only, or logic exists only for, logic exists but whom? Only for valid. It means logic not exist for invalid strings. Remember that I said only for valid because this is RE but outside the recursive. These languages in between this pink and blue, you do not have the logic for invalid string. Third one, not RE means outside that pink. It means logic not exist for valid. Logic not exist for which strings? Valid. Valid strings we do not have a logic. It means valid may or may not have a logic. That's also important. Not or means don't say that. Logic also not there for invalid, don't say that. Logic may be there for invalid or may not be, because I'm only talking about valid. Logic is not there for valid. Logic is there only for valid. Logic there for both valid and invalid. Undecidable means the outside decidable. Outside decidable. Here logic is for both valid and invalid, right? But this one you will never have the logic for both. It might be there for only valid, it might be there for invalid, but you will not have the logic for both valid and invalid outside. So here the undecidable means it is guaranteed that you will never get a case logic exists for both valid and invalid. Here it happens logic exists either for valid or for invalid, that's it. You will not have, or there is one more case, logic may not exist for both. Logic may not exist for both. So I missed that point, but I'll write here. Writing logic exists only for valid, this is one case, or only for invalid, or not exist for both. Logic not exist for both valid and invalid, that's also one case. These three cases may happen, because one case I have to ignore, that's logic exists for both valid and invalid here. If it is outside, anything could happen out of that situation. RE language means simply guaranteed logic exists for valid strings, but don't say only for valid. We don't know logic exists for invalid or not. If it exists, that comes to recursive. If not exist, logic not exist for invalid, it is here. Logic exists for invalid, it is here. Anyhow, all these string, all these languages, when you look at the valid strings, the logic exists for valid, no doubt, from here to pink, within the pink box. Okay, but only the doubt is, do you have a logic for invalid or not? If you have the logic for invalid, it will be here. Logic for invalid, if you don't have, it will be here. But anyhow, for the languages which are inside the REL's class, logic exists for a valid string, but we don't know logic whether the logic exists for invalid or not. That depends on which language you are talking about. Look at the cases and please note down the points clearly. Yes, if you have any confusion here, you can always come to discuss and ask the doubts. That's a very important point. Fine. This is about undecidability and decidability of languages. Those people who are having these 5 points, and very easy for you to just classify the various languages and put into proper place. Okay. Okay. As I told, what is decidable language? Remember, what is decidable language? Logic exists for both valid strings of L as well as invalid string. And if you are saying L is decidable language, logic definitely exists for both valid and invalid strings. It means when you are designing a Turing machine, give a string W, W belongs to L or W not belongs to L. Assume this TM accepts L. It definitely halts, but that halts at final. It is also going to halt, but that halts at non-final. This is how TM always halts situation happens. The logic is for both valid and invalid. So any string you give, you can prove that how it halts at final, how it halts at non-final. You can easily describe the decidable languages with the Turing machine behavior. Now, you may ask, sir, can you give me some of the decidable languages? Very simple. In front of you, you have many languages. In front of you, already seen lot. like L is equal to A star B star is a decidable language. L1, L2 is equal to W power R. The W belongs to A comma B whole star. As it is CFL, right? If it is CFL, it is definitely recursive. It means decidable, right? It is regular. Every regular is what? Decidable. Every CFL is what? Decidable. And not only this, A power n, B power n, C power n, it is a context sensitive language. Just design Turing machine, right? We have a Turing machine with bounded tape length, means it is a linear bound automata. Actually I have designed for linear bound automata. So language is context sensitive. And all these languages are what? Decidable. This is decidable. It is also decidable. It is also decidable. Decidable, another name, do not forget, it is recursive. What is it? Recursive. Likewise, you have many examples that we will see soon. Another language is RE but not recursive. RE but not recursive. What do you mean by RE but not recursive? It means for logic exists only for valid strings. It means invalid strings, you do not have a logic in the language. Okay? If L is RE but not recursive, then the logic is only for valid strings. Invalid strings, you do not have a logic. You do not have logic. That's why you don't say that L is recursive. We are saying RE which is not recursive. I have a logic for valid, but I do not have a logic for invalid. Then this question comes. Okay? It's very simple. When you design a TM, you give a W belongs to L. You can clearly say it halts at final, but W does not belong to L. I don't have a logic. Then I can't say that whether it halts at non-final or never halts. It might be never halting for many situations, so I am not able to form it. Okay? That means at least one situation you will have that never halts situation. That's why you are not able to form a logic. Okay? Now you may ask, can you give me some examples that are RE but not recursive? RE, I have a Turing machine, but I don't have halting Turing. If any language we call it as RE but not recursive, it means you have a Turing machine, but you don't have halting Turing. There are many languages, but do not worry about the meaning right now. Simply like set of all regular languages. I'm not talking about one regular. One regular is already decidable, but it is a set. Like set means I have language 1, language 2, language 3, and so on. Like this. Every L is here regular. Every L is what? Regular. It's simply you can call it as something like L such that L is regular. Oh, with this you can build a Turing machine, but you can't have halting Turing. Right? Whoever is non-regular, you will not have a logic. Some non-regulars you will have a logic, but not every non-regular. Right? Like not RE is also not regular. Not RE is also not regular. You don't have a logic. So very important point. Not only this, set of all CFLs. Don't say one CFL. One CFL is already decidable language. But when the language which has the context-free languages, set of all context-free languages. I'm not saying CFLs is RE but not recursive. What I'm saying, this set which has all CFLs. Like I have a CFL1, I have a CFL2, and this set is having Turing machine, but you do not have halting Turing machine. Likewise, set of all decidable languages, set of all context sensitive languages, set of all RELs, all that languages comes under here. Okay? Many things are there. Non-RE in the sense, logic do not exist for valid. We don't know logic exists for invalid or not. That's a secondary. You may have the logic for invalid, we don't care. Here, logic does not exist for which strings? Valid strings of the language L. Whenever you do not have the logic for valid strings, then we say that language is non-RE. But logic may exist for invalid. We don't worry about it. May exist, but still the language is what? Non-RE. When the language is non-RE, the valid strings of the language you do not have a logic, so you end up with this. You end up with this answer, non-RE. Non-RE. So do you have any such situations? You want to know the examples. Do you have any such situations? The language is non-RE. Language is non-RE. Very many examples. Set of non-regular languages. Can you have every non-regular there is a logic? No. When you have a set which is, let's say, NR1, not regular, assume that not regular, okay? Not regular 2, not regular 3, not regular 4. Can you guarantee every non-regular has a logic? If you can guarantee, then I may say that it is having Turing machine. This language has a Turing machine. A language in which every string is a non-regular. It's not a string actually. It's another language. Now see, this is the language in which every element is another language. Do you have a logic for every non-regular set? Some of the not RELs comes here, right? Within the non-regulars. That's why this language is itself not. Not only this, set of all not CFLs, set of all not CSLs, set of all not REs. That is also one not RE is already not RE. Every not RE is there in the set. Definitely it is going to be not RE. Why these languages are not RE? Because in which at least one language you will see not RE. Set of all not CFLs. CFLs outside, CFLs class outside. CSLs may come, recursive may come, REs may come, not REs. Here not REs are there. So if any language, if you see one not RE as a member, then you will see whole language is not RE. That property somehow it applicable here. What about undecidable language? Very important. Who is called as undecidable? Any language who is not recursive, who is not decidable, okay? Who is not decidable. That means you cannot prove that both valid and invalid have a logic. That means I told three cases. You may have a logic only for valid, you may have a logic only for invalid, or you don't have a logic for both valid and invalid. In these three cases, the language may come. Undecidable language is outside the recursive. It can stand anywhere. It can stand anywhere. Okay. Undecidable language, basically it is either RE, which is not recursive. That's the one place you may see the language, or not RE or non-RE. In these two situations, an undecidable language is present. So every non-RE is undecidable, every RE but not recursive undecidable, but undecidable need not be RE but not recursive because it may be non-RE, or it need not be non-RE because it may be RE but not recursive. So very important, how do you imply these statements? Undecidable language is either not RE or it may be RE which is not recursive. So if you look at the classes outside the recursive languages, it can come anywhere. It can come anywhere. The meaning already I told. There are three cases. In which the logic only there for valid, or logic only there for invalid, or logic is not exist for both valid and invalid. Examples already you know, right? You can take any RE but not recursive or not RE. If you take RE but not recursive, that is set of all regulars. One example I am taking. This comes under RE but not, this is undecidable. Why undecidable? It is RE but not recursive language. RE but not recursive. So I can call it as every RE but not recursive is what? Undecidable. UD I am using, UD word. Okay. Another one, set of all not regulars. set of all not regulars, which is definitely not RE. When it is not RE, that is also UD, undecidable. So undecidable languages might present in RE but not recursive, or it may present in not RE. Both the situations, all the languages comes under as undecidable. So when I am saying this language is undecidable, will not have a clarity. Why? Because I may be talking about this language or these languages. Okay, so this set, this is the language I'm there is one problem we may face. I'm saying again, look at carefully what language I'm talking about. I'm not talking about regular language. I am talking about a language in which all regulars are there. The way you present is very important. If you see only this word, sir, why sir is saying that regular is undecidable? I am not saying regular is undecidable. I am saying the language. I am saying the language is undecidable. Which language? That has all regulars. I am not talking about one regular. Remember, here I am saying the language is undecidable where that language has all not regulars. Remember the point. Is that clear? Right? I know the regular language is decidable. That doesn't mean that a language which has all regulars is decidable. There is a much difference here. There's a much difference here. Okay. Now you know this RE language. RE language means, you know, valid string. Definitely logic exists. Logic exists for valid strings. Logic exists for valid strings. But do you have a logic for invalid? Depends. If it is inside recursive, you will have a logic for invalid. If the language is outside the recursive class, then logic not exist for invalid. But in either case, whether it is inside the recursive or outside the recursive, logic definitely exists for valid. That language is called as what? RE language. Logic definitely exists for valid strings, but invalid strings logic may exist, may not exist. What is the RE language? It's simply whenever you have a Turing machine, you can say the languages, but it may stand in regular or CFL, dcfl. That depends on what is that language you're talking about. Okay, so what are the RE languages you have? You can take many examples like all the recursives, even a plus b whole star over a comma b. It's regular, right? If it is regular, is what? RE. You can take a power n, b power n, c power n. What is CSL? What is CSL? Even regular is what? RE. CSL is what? RE. But there are many other languages. What else you have? Recursive, right? Some language like, let me write, set of all regulars, which is not even recursive, which is something directly RE. Actually, this language is what? RE but not recursive. But you know, RE which is not recursive is also RE. You can say that, right? RE but not recursive, we clearly known that it is RE. There are many, you know, languages outside the CSL, inside the recursive, but I am not disclosing here. There are many. Now, this is the time to learn the closure properties. As we know that closure properties, let's practice them to have a clarity between the various classes. L1 and L2 are two RELs. Union is already closed, right? REL1 union REL2 is always REL because union is closed. Union is closed, so we say it is REL. Do you have any option here? REL? Can you say recursive? No guarantee. Can you say always RE but not recursive? No guarantee. Can you say always not RE? No guarantee. We don't have option. We don't have option. Okay. So remember this. Don't choose blindly somewhere. It will not work because we know it is REL, but it may be recursive. We don't know. It may be outside the recursive, inside that RE but not recursive class. Okay. Be careful. It is REL, we know, but really we don't know whether it is recursive or not, whether it is regular or not, whether it is CFL or not. We don't know anything. Second, two recursive languages L1 and L2. That means recursive union recursive. We know it is recursive 1 union recursive. What should be the result? Recursive. When answer is recursive, you can also choose RE. So here choose the proper one. Recursive definitely correct. RE but not recursive. Completely different places, right? If once you say recursive, it never be RE but not recursive, you can say that. And never be not RE because outside the recursive class. RE you can say. Because once I say it is in recursive, it is in Delhi, definitely it is in India, right? So this is how you can choose. There is no option for RE. If RE is there, I could have chosen that too. Okay. Next, L1 is recursive and L2 is RE. One is recursive, other language is RE. Recursive, you have alternate Turing machine. RE, you have a Turing machine. When you are combining these two languages, it's guaranteed RE might dominate the recursive. Finally you will get RE, but you may get recursive, may not. That depends on again what RE you take. Within this RE, if you take recursive, definitely recursive union recursive, you may get a recursive. But within the RE class, you don't know which language, which RE language you consider. That's why we can guarantee RE. Which one will match? Recursive will not match. Nobody, right? RE don't have the option here. But if you have RE, you should choose that. Very simple. L1 is recursive and L2 is DCFL. Here you are doing DCFL union recursive. DCFL union recursive. Which language you get? See, recursive you cannot assume DCFL because recursive may be non-DCFL. But DCFL you can assume recursive. Recursive union recursive, you will have recursive. You can guarantee you will get a recursive language. You can design halting Turing machine for that, recursive. But do you have, every recursive is what? RE. RE you may choose if you want it, if you don't have recursive here. There is no RE option, right? So you can't choose. So recursive is there already. So recursive union DCFL is what? Recursive. Similarly, recursive union regular. You can conclude. Recursive union regular is recursive. You can guarantee halting Turing machine there, but you can't guarantee DFA is there. Recursive union regular, which is recursive, guaranteed. I'll just write some of them here. Recursive union finite. Recursive union DCFL. Recursive union CFL is recursive. Okay. It's based on the properties that you have. Okay. Recursive union CFL is recursive. No guarantee of CFL. No, there's no meaning to this option. REL union regular. Now REL union regular, same applicable. Here RE comes out. Okay, there is no RE option. REL, recursively enumerable language, union regular. Which one you will choose? Always regular. Sorry, always REL. Sorry, always REL. You have a Turing machine for the 11 language. Other language you have a DFA. When you combine these two languages, in worst case, the Turing machine will help you all the time. All these three options cannot guarantee, but you have to look at the option RE. If you have an RE, recursively enumerable, please choose that. CFL union REL. So again, you have Turing machine after doing the union, that is guaranteed all the time. But is there any possibility of context free? Yes, possibility is there, but do not say always. Here, need not be, may or may not be CFL. Possibility is there. Why not? Okay, so here these three options are wrong. You will go to none of this. Always REL. Recursive. So now we'll come to the complement. Union you understood, right? You can apply that union for various languages, you can understand. Now we come to the recursive. complement of recursive. The first time we are trying to understand the recursive complement, but we know it's a close, right? Then what should be the answer? Complement of recursive. How do you prove it basically? You have already halting Turing machine designed. The S you make it no, no you make it S, then you have designed the machine for complement. Again you have designed halting Turing machine. There was previously logic exists for valid, valid of L, valid strings of L. Now you will say that the same valid strings of L is nothing but the invalid strings of L complement. It means the same logic you copy paste. You will get again a recursive. So recursive guaranteed. When it is recursive, you can also say RE, but it's not by implication. Only one side. Remember that, only one side. So you can say here recursive complement is recursive. You can say here two directions, but here only one direction helps. Okay. Look at here, is there. That means only one side we are talking about. You find only if they ask, only this one should be chosen, not this RE. Right now for this question, RE is also correct option. RE is not. What is RE but not recursive? This language. Now RE inside the recursive enumerable class, but outside the recursive class. That language is taken now. You do the complement. What is the meaning of doing the complement? See here, RE but not recursive means logic exists only for valid. Invalid we don't have a logic. You know this is a one language, right? For this language, logic exists only for valid. When you do the complement, now I have the logic for valid. I don't have the logic for invalid. Now this invalid will become the valid strings in the complement. Invalid, see that. Let's say this is L, right? This is L only, na? Complement means. Now we are trying to find the answer. See, valid, invalid. Which language you are talking about? L. L we are talking about. L means RE but not recursive. The valid strings we have a logic, L. Invalid we don't have a logic. When you go for a complement, this invalid become valid there. Valid we don't have a logic. When we don't have a logic of valid, that will become not RE, right? That will become not RE. We don't worry whether the valid you have a logic or not. This valid of L will become invalid of L invalid of L complement. Invalid. This you have a logic. But L complement, valid strings of L complement, we don't have a logic. How you build a Turing machine? Impossible. That's why we call it is simply not RE. Will directly go outside the RE class. That language is called as not RE. Okay, remember this, RE but not recursive. Its complement goes outside directly, not. And explanation is here. So not RE that you will choose here. You can't choose any of this. L is RE, complement of RE. So RE language, RE means the logic exists for valid, but we don't know logic is there for invalid or not. Come to the point. The RE complement, we know that it is need not be RE, that's why it's not closed, right? Need not be RE. But what is the meaning of need not be RE? What is the meaning of that? Complement of REL, need not be REL. Look at that. We have within the REL class, this is all RELs. These are, let's say, all recursives, all recursive languages. Okay. Now, you take this language, do the complement, you will come here only, right? You will stay here only because the complement of recursive is right? It's a L complement here. Now I'm taking something A here, the language. When you do the complement, this is the RE but not recursive. What are the languages here? RE but not recursive. It will go outside. That is a not RE. What are they? Not RE. Look at now, we have two languages here. One type language is recursive, other type language is outside the recursive, which is RE but not recursive. Now these languages, their complements are inside the recursive. These languages, their complements are outside the RE. So you have two answers. Either recursive or not RE. Only two situations happens. There is no language which comes to the RE but not recursive class. So it's a very easy now to answer either recursive, it may be decidable, or it could be non-RE or not RE. It means answer might be standing in recursive class or outside the RE class, right? But you see here, never be this one RE, but never be this, never be language in this class. That means never be, this was a PYQ, never be RE but not recursive. This language is never be in this position. Once you take the language from anywhere here in this box, either L or A position, it never comes to this A position. Position means this outside the circle, within the box, anywhere. Fine. These are the three different answers. It will help you for the exam point. Which one you will choose? Recursive you can't choose. Maybe recursive, right? You can't say always recursive. Can you choose RE but not recursive? You have to say never be RE but not recursive. That's why you can't choose. Not RE. Can you say always not RE? No, sometimes only. None of this is the best option. Okay, none of this. If they ask which of the following is possible, recursive possible, not RE possible, you can't choose this one. Which of the following is possible, which of the following is true, then you can't choose any one. Only none of this you can choose. Which of the following is possible, then recursive is possible sometimes, not RE. So read the question carefully when they are asking which of the following is possible when you do the complement of RE. Then you have to choose A and C. Okay. If L is undecidable, then complement of L. Complement of L. What is undecidable? Tell me. L, you are saying UD. When you do the L complement, you are doing UD complement. UD means there are two possible languages, right? One is RE class, which is not recursive. This might be possible, right? Either this one you are doing the complement, or you might be doing not RE complement. There are two situations. If you are going to do this one, RE but not recursive, its complement definitely not RE. When you do the not RE complement, you may get a not RE, or you may get the RE but not recursive. You can go back to that. There is a possibility in the overall, there is a possibility RE but not recursive. You will never come to recursive. You will never come to recursive. That's guaranteed. So again, not RE or RE but not, that is only undecidable, right? You will get UD back. Understand theoretical concept. UD complement, you will get back to UD, but somewhere outside the recursive will stand. I don't know where exactly, depends on the language, but it is UD complement is UD. Now, can you say recursive? You can't. RE but not recursive, maybe sometimes, but not all the times. Not RE, maybe sometimes, but not all the time. So better to go for UD. If you don't have the option, go for none of this. Go for none of this. Sometimes some people may say not decidable. That's fine. Some people may say UD means what? Not decidable. Not decidable means not recursive. So in the exam, they may try to confuse with very different statements. L has no halting Turing motion, but Turing motion may exist. What they are saying is L is not having halting Turing motion. Means you may have the motion or you may not have the Turing motion, but you don't have halting Turing. Many other ways to define that L. Great. If L is non-REL, what is the complement of non-REL? Non-REL. Non or not, both are same. Not REL complement. See, when you are having RE, all REs here, right? All RELs. These are all recursives. All recursives. These languages, when you do the complement, let's say L, you go outside. But when these languages you do the complement, let's say A, it might be here sometimes. If you take the B, it might come here back, because the same language you can come back here, B complement. So when you look at this not REs, their complement might be here, because valid and invalid both might not have a logic. Here B, the valid you don't have a logic, but invalid you have a logic. That's why in a complement the valid you will have a logic. In a complement, the valid of B complement you may have a logic. So you are coming back here. The same language that went L to L complement is coming back. So not RL complement, what happens now? Either it might be not RL or it might be RE but not recursive. Very clear, just undecidable. Not RL complement, what else I can say? Not REL. Look at that. The answer is either not REL or REL but not recursive. It could be standing anywhere here. REL but not recursive. Outside the recursive anywhere. It means simply you can say UD, undecidable. But not REL implies undecidable, but undecidable need not be not REL. So remember that not REL complement, just don't say not REL. It should be not REL or REL but not recursive. When I look at this two, oh, you are talking about some undecidable, some outside, right? From this point to this point is actually called as UD languages. Fine, recursive you can't choose. Only sometimes. But you can say undecidable language. That is either not RE or RE but not recursive. Very important example. Now, we'll come to decidable languages. Let's go quickly. Which of the following is our decidable? Finite language over sigma. Is it decidable or not? Because every finite language is regular, so every regular is decidable, no doubt. A regular language over sigma, decidable. Context-free language is already in the recursive class, right? So all the three are correct. These are decidable. These are decidable. Not only this, context-sensitive, recursive. RE you can't say because it could stand anywhere. Which of the following is our decidable again? Complement of means is infinite, no doubt, over sigma, but regular only, right? Complement of finite, every finite is regular. Complement of regular is regular. We know every regular is CFL, every regular is dcfl, every regular is recursive, so we can say decidable. It is decidable. Complement of finite is always regular, so decidable. Complement of regular is regular, every regular is what? Decidable. Complement of CFL may not be CFL, but it's going to be context sensitive language. But this CSL means decidable only. Decidable, another name is what? Recursive. I can say it is a recursive language, so decidable. Okay, so remember this point. Complement of CFL need not be CFL. We know complement is not closed for the CFLs, but complement operation, when you apply over the CFL, you will always get a decidable language. You will always get decidable language. I'm not talking about operation is closed or not. I'm talking about result of the language, is it decidable or not. Okay, so understand the statement. Which of the following is or are decidable? This is nothing but set of, it is a set of strings, means finite language, right? Set of symbols only. How many symbols are there? 2 symbols. It means finite set. Every finite set in the world is decidable. Star is universal language. It's a regular language, even though it is infinite. So every finite set is decidable. Every regular is decidable over sigma star. Over the same sigma you take. Nothing but set of all languages. You already know set of all regulars only, it is undecidable. Now set of all languages here, not RE also can come here, then you are so danger. Not decidable, not decidable. Okay, next, set of finite language. Unfinite language is decidable. Now in this is a one set, right? Here finite language 1, finite language 2, finite language 3, every finite language is there. Now this set is different from what you are writing. This set is decidable, no doubt, because it is a finite, right? It is the finite, so you say decidable, no doubt. But this set, no more finite, it is the infinite set, where every member is a finite language. This is, you can't say finite, because set of finite languages is going to be something different. I told you already, RE but not recursive. What is the language name? RE, but which is not recursive. Why did you get RE? Because every string you have a logic. How do you know the logic? Every finite language you have a Turing machine. You know the DFA is already there. I'm just saying Turing machine. Every finite language you have a Turing machine, because already you know you have a DFA. That means in this, all valid strings, whoever present here, who is not present, finite language, that I can't guarantee you have a Turing machine. But every finite language I can guarantee you have a Turing machine. Means every valid string means it's not a ABC, it's a language here. Here every valid string has a logic. That's why RE but not recursive, because its complement has no Turing machine. Set of infinite languages, this is its complement. Its complement is here. Here you have an infinite language, you have another infinite language, and infinite language could be any, right? It could be outside the finite class, anywhere. Might be inside regular, inside DCFL, inside CFL, CSL, recursive, REL, or in languages anywhere. So this is very, very difficult. Straight away not RE. Anyhow, it is undecidable. Both are undecidable. This is undecidable only. It is also undecidable. But undecidable, there are two classes. One class is RELs, which are not recursives. Another one is not RELs. So where it stands exactly, I have written the answer here. Okay. Set of regulars, it is also undecidable. Again, I am saying I am not talking about A, B star. This is decidable. But I am talking about all the regulars are there in the language. That language I am talking about. Let's say this language something like A star, A B whole star, maybe over A comma B I am talking about, A plus B whole star, and such languages I am talking about. Every member is a language. Now every regular you can design, every regular language you can design a Turing machine. But its complement is going to be, this complement is going to be set of non-regulars, set of non-regulars, set of non-regulars, that you don't have a Turing machine. But what is this? It is again RE but not recursive. RE but not recursive. Set of non-regulars. Oh, in this you may have a not RE. That makes problem. Here not regular. Not regular. One. How many not regulars you have? Infinite. In this not regulars, you will also see not RE language. You see one not RE language as a member of the language, then the whole language is going to be not RE. Anyhow, this is not RE. You don't have a logic for everybody in the language. That's why it is undecidable. See that all the problems are undecidable, but which undecidable is very, very important. Okay. Next, which of the following are decidable? Again, one CFL is decidable, but set of all CFLs undecidable. I can say that when see one decidable called as decidable, but when you combine all decidable as one set, within the set you kept all decidable. Now this set is so big. Now that problem is again undecidable. So all these are undecidable only, no doubt. But which undecidable it is? Every CFL, do you have a logic? Here, this is the language, right? I'm not talking about A power n, B power n. I'm talking about so many CFLs here. CFL1, CFL2, so on. Every CFL, do you have a Turing machine? Yes. Then every valid string you have a logic. This is a string now. One string is here, a language. Here another string, that is a language. So every valid string you have a logic. Means you have a Turing machine, but its complement is set of all not CFLs. Invalid strings of this one means its complement only, right? So not CFL, do you have a logic? Every not CFL, no. That means this is going to be RE but not recursive. Only valid strings you have a logic. Invalid strings, no logic. Set of decidable languages. See, one recursive, let's say this one. D1, decidable language, decidable language, decidable language, decidable language. Every decidable is fine, you have a logic, but its complement set of undecidable languages. Can you guarantee every undecidable has a logic, or every undecidable has a Turing machine? You can't, right? So this is again RE but not recursive. Set of RE, same, its complement is set of not RE. Every not RE you can't guarantee a logic, but every RE you can guarantee a logic, so it's also same answer. All are undecidable, but all are here RG but not recursive. So this is the one problem. See now, when I draw the diagram, carefully look at, this is what all, I can say another way better, set, box name it is, remember that, it's a box name, set of all finite sets over the sigma. Here you have F1 and F2, I can't say that, right? I'm just keeping the dots, I don't want to keep the names. These all are languages, so many languages, infinite here. And we have set of all regulars. For simplicity, assume this is a box, this is a B box, something like that. Now, I'm just omitting all, I'm just going directly set of all recursive decidable. Recursive languages means sets. Now come to the point. Here I'm just coming to one class that is very special class now, that is set of all RELs. Set of all RELs. Now think about the language that I am taking. Here you see the one problem here. The one problem, one dot, that's a one problem. The whole box is going to be a problem here. Set of all finite sets is the one language now. Another language, set of all regulars, is another language here, created as a language now. Similarly, set of all decidable languages, set of all context-free languages, set of, that's a one language that's lying inside the RE but not recursive, outside the recursive class, and inside the RE is lying as a one language. Is that clear? This language is standing here because the every finite you have a logic, that's a valid strings, the language. Every infinite you can't say the logic because invalid of this set is the infinite language. Valid of this set is finite language, invalid of this set is infinite language. So every valid you have a logic, every invalid you can't give a logic. That's why standing in RE but not recursive. Understand what's happening here. Understand what's happening here. Fine. I hope you got a clarity why I'm saying these languages are very important for you. Now go to the next question. Which of the following is decidable? CFL, decidable, CSL, decidable. Decidable because it's another, CFL is actually decidable because it's there inside decidable class. Recursive language is decidable language only, not RE. Its another name is, not RE implies what? UD. Another name implies UD, undecidable. Which of the following is decidable? Complement of CFL is a CSL, so I can say a decidable. Recursive, another name. Complement of CSL is definitely CSL, so CSL is recursive. Complement of recursive is recursive only. The recursive, another name only, decidable. Okay, another name is what? Decidable. Complement of not REL, which is actually UD, undecidable. But undecidable, it's the opposite of decidable. Very clear. So which are decidable now? C, B, A, B, A, but D is not. Okay. With this, we are left with one topic: decision properties. What is decision properties? There are various topics you have learned: regular languages, context-free languages, deterministic context-free languages. What else? Recursive languages and RE languages. So decision properties are very important properties where you are going to apply using certain restrictions or certain operations. Now let me tell you, I'm going to ask some question like this. Membership. This is one of the decision property. It's a problem. Here you are going to check some property. Membership problem means I'll give you string, I'll give you machine. Is that string accepted by the given machine? You have to check. Without looking at the machine, using algorithm, you have to check. Using algorithm can look at, but not you. Okay. Is there any algorithm commonly it can look at your machine and take the string and verify the given string is W belongs to L of M. M is given and W is given. M is given and machine is given, DFA and PDA, anything, and W string is given. Now you have to verify. Can you say yes or no? Yes means W accepted by machine. No means W not accepted by machine. You have any algorithm for that? Okay. Likewise, you have a lot of problems, membership and halting problem. The various decision properties we have. Emptiness. We have a lot of shortcuts for them, but right now just I will talk about are they decidable or not, as they are going to take a lot of hours to complete. Even membership problem only take 1 hour to understand whole property. Totality, equivalence, very important decision properties. In case if you do not know, learn these properties will help for the exam point of view. And set containment. Two things I can say very clearly, all these problems are decidable for regular languages, that for finite automata. All these are undecidable for Turing machine. It means undecidable for RE languages, recursively enumerable languages. So remember this point, note whether you know the concept or not. This note is very important for you, whether you know the definition of this property or not. Note all these 8 problems, all are this only I am talking about, all are decidable for regular languages or machines, finite automata, if you are taking finite automata for regulars. This all are undecidable if you are going to take Turing machines or RE languages, RELs. Remember these 2 points, but remaining you should know exactly how many are decidable, how many are undecidable. Okay, that is challenging for you. Okay, let me discuss them one by one. Some of them it might help you. Which of the following is decidable for regular languages? Okay, is or are, could be sometimes more. Membership is decidable? Yes. Finiteness, emptiness, totality. All problems are decidable for regular languages. This is what the question you may face in the exam, but there are some variety of questions also there. We'll see that. Second, is decidable for dcfls? Here, very important point, some may not be decidable for dcfls. You should know about it. Some are not decidable. Membership, you have a CYK algorithm for dcfls, CFLs, so it is decidable. Finiteness, suppose dcfl is accepting a finite language, so even till CFL you can check using dependency graph. You can check, you can write a context free grammar, you can draw a dependency graph, you can check finiteness concept. Emptiness, so for especially DCFLs, this emptiness is decidable. How? Including CFLs. You can simplify the context free grammar after converting into context free grammar. If you left with a single production, it is a non-empty generating. If you don't have any production in the grammar, after simplifying, you can say it is generating empty. Anyhow, it is also decidable. Totality. So this one, especially this one, it is totality means, especially totality means is language accepted by DFA equal to sigma. Now, how do you do that? Especially for this, is the same as if and only if is, I can, instead of saying here if and only if, I'll just say L of DFA, sorry, DPDA, right? I'm very sorry, sometimes I do mistake. Let me write again. I'm talking about DPDA, not DFA. DPDA, DCFL I should write actually, is sigma star. To do this, what I do, I have a logic. If you want to check L is equal sigma star, you can see that L complement equal to pi. Both are same, right? What we do, instead of checking this, is L of dpda complement equal to pi. Why I am doing this? Because dcfl complement is dcfl. That's why checking emptiness for dcfl is already we have a decidability, right? But this thing you can't apply for context-free language, because context language complement you may not get a cfl back. You will get a CSL, for that emptiness is already undecidable. It's very important. This totality problem is decidable for DCFLs, but not decidable for CFLs, context-free languages. Okay, so this point you remember, totality problem is decidable because emptiness is already decidable. Complement of DCFL you will get back to decidable DCFL. That's why you are checking is L of dpd equal to pi. Complement of L is again DCFL only. Fine. For context-free languages, membership decidable for till halting Turing motion. Finiteness, you have dependency graph. Emptiness, you have a simplification of the grammar. Totality, just now I told it is undecidable. Okay. Now, which of the following is decidable for recursive languages? Recursive languages, two are decidable. One is membership, another one is halting. Because of halting, you can verify whether the given string is valid or invalid. Okay, because it always halts. So membership is only decidable, remaining all are undecidable for halting Turing motion. Also you can say recursive languages. Okay, and it is same for even linear bound automata and also context sensitive languages. Remember these 8 properties, 8 decision properties that I have disclosed, I have explained in the beginning. For halting Turing motion and linear bound automata, they are similar, they are same. RE languages. RE means Turing motion. Turing motion, I told, all these problems are undecidable. Only the difficulty that you may face, which undecidable? Is it outside the RE class or inside the RE class? That's RE but not recursive class. So that's going to be interesting. But anyhow, all are undecidable only. They are not decidable. All are what? Undecidable only. Undecidable problems. Okay, this kind of questions you may face. Now, how do you apply this kind of questions in the exam? Very simple. M is a DFA. First, have you understood this problem? Don't assume I have given you DFA. Actually, what I have given lot of machines. So my language is having only DFAs. Now you need to check. In my language, all these machines are accepting AB. But in general, you need to understand the machines, the DFAs. These DFAs may accept AB or not. Whenever it accepts AB, you need to say yes. Whenever it is not accepting AB, you should say no. That is how you can collect this language which is having only the DFAs which are accepting AB. But now this set of DFAs are accepting AB. This language is what? Is it, can you say first regular? I am not giving you one DFA, I am giving you n number of infinite DFAs. How you can understand infinite DFAs with one DFA? Impossible, right? Now the question is, if everybody has a logic, if this DFA is accepting AB, you already have a membership algorithm, right? You can apply on every machine membership algorithm. If it is accepting AB, throw into the L. If it is not accepting, throw into L complement. So L and L complement, valid and invalid, both you are able to decide. You are able to provide a logic using membership algorithm. So to understand this, you need to apply membership algorithm, that is CYK algorithm. If you wanted to learn, so decidable. Can't choose anybody. Already it is decidable, right? Once answer is decidable, this answer never comes to here. Okay. Look at that. This TM that accepts AB, it's a membership. We know membership is undecidable. What exactly undecidable? Suppose TM accepting AB. TM accepting AB. That means definitely halts at final. Definitely halts at final. It is not accepting AB. We don't know what happens. Means whenever it is valid, whenever the TM accepting AB will have a logic. Whenever not accepting AB, we don't. That means In L, whatever the machines present, you will have a logic why it is halting at AB, why it is accepting AB. But whenever the machine is in L complement, you don't know, you don't have the proper reason, because that may halt at non-final, that never halts. So now valid strings of L means all the machines in L you have a logic, all the machines which are not in L don't know what logic you have, because they are not accepting AB. Okay, it is going to be RE but not recursive, even though it is undecidable. But what kind of undecidable? RE but not recursive. But RE but not recursive, definitely RE, right? Is RE correct? Decidable wrong. RE but not recursive correct? Not RE, you can't choose. In the exam, you have to be careful which one you're choosing. We know RE but not recursive. If it is RE but not recursive, it is already RE. So either in the exam, you may see this one or this one. If it is MSQ, you may see both. Okay. TM that accepts epsilon. Empty string means what? Epsilon. Again same. Membership AB or epsilon doesn't matter. It is a string. It is a string. Whether it is W or AB doesn't matter. It's a string. When that accepts some string, it's a membership algorithm. What is it? Membership. Just now we have seen membership. Membership means membership for TM. It is RE but not recursive. The same as the previous problem. No confusion at all. Okay, somebody has given epsilon, somebody has given AB, somebody has given W. It's always same. So that's RE but not recursive. Don't choose it. Okay. That accepts only epsilon. It's different. Only means somebody saying M such that L of M is equal to epsilon. That means that given a set of machines are accepting only epsilon, nobody else. Now here there are so many machines in the language, M1, M2, M3, infinite machines, let's say. All the machines which are there in the L are accepting only epsilon. Only remaining all should be rejected. First, accepting epsilon, it's fine. First, do you know why this M1 present here? How can you guarantee? Because I'm not saying M1 accepts epsilon. I'm saying M1 accepting only epsilon. How? My question is only for this M1. How do you know? L of M1 is equal to epsilon. If you want to say this, you should prove that this M1 accepting epsilon. If you want to prove that, there are two things. M1 accepts epsilon, not enough. M1 should not accepts all remaining. Now this is the problem. Now if you want to say not accepting all remaining strings, you don't have a logic. That means for this checking, you don't have a logic. That means this problem itself not RE. What is it? Not RE. I don't know why this M1 included here with the I don't have a logic, because I can't prove it that M1 does not accept all the remaining strings. I may check M1 accepts epsilon, does not, it's not enough. So I have to check M1, is it accepting only epsilon? Only word is making complicated here. That's why it goes to not RE. Then look at, you can't choose A, you can't choose B, RE but not recursive. I'm already saying I don't have a logic for even valid members. Valid members means here the machines of L. Not RE is the proper one here. Okay, correct one. Yeah, very famous one. All the context-free grammars are there in my language. Like in my language, CFG1, CFG2, but they are all ambiguous CFGs, not all CFGs. Ambiguous CFGs. When this is ambiguous CFG, do you have a logic? Logic exists or not? Logic is there. Logic there. What logic? At least one string which has more than one parse-string. If that is ambiguous, I can end up with my logic. But if it is not ambiguous, definitely I don't know, right? I may not end up, because every string has exactly one parse-tree. Every context-free grammar which is ambiguous, we will have a logic. That logic is, for some string, you will definitely have more than one parse-tree. So you can put them in lexicographical order, keep checking for every string how many pass states are there. If you get more than one, then stop there. Don't check any other remaining string. That means you will definitely have a string that has more than one pass string. So because of that, every context free grammar has a logic. Then we can say that, okay, not enough. What about invalid string of L? Invalid of L means the context free grammar who is unambiguous. Ambiguous, one context free grammar who is unambiguous, if it is generating infinite strings, how will you end up it? Very difficult. So here you have a logic, so we can say RE but not recursive. Why did you conclude this? Because invalid of L means the context free grammar who are unambiguous, I don't have a logic. That is the reason I concluded I have a Turing machine but I don't have halting Turing machine. I kept clearly RE but not recursive. Whenever RE but not recursive, I can say RE because Turing machine anyhow there, decidable and not RE, you can't choose. Okay, RE but not recursive, definitely RE. But don't write other direction. When I am saying RE, don't say always which is RE but not recursive. Maybe RE but not recursive, maybe recursive, depends on which RE you are talking about. Oh, TM has at least 2 states. For this, you don't need to run the machine, right? Just look at the configuration, how many states are there in TM. So this is trivially possible to check. If TM is not having more than or equal to 2 states, less than 2 states, that is also possible. L is here, L complement is nothing but TM which has less than. Here at least that one is opposite, less than 2. Any of both will have a logic, right? At least 2 means even though it has 100, just check, do you have a 2? Then stop there, right? You know, finding the number of nodes in the graph, anyhow TM is always having finite configuration, so that's definitely. You say decidable, when it is decidable, what is it? Both are decidable, L and L complement. Okay, decidable, when L is decidable, L complement is decidable, then definitely it is, every decidable is what? RE. Only I am asking is, if and only if I am not asking. Okay, RE. Oh, I can't say RE but not recursive because I know it is already decidable. I am only choosing RE because it's already decidable. Once it is decidable, it is also RE. Oh, at least 2 strings. Now TM should have, should accept at least 2 strings. If I am going to keep some machine here, TM1, TM2, see, why did I keep this TM1? Because it is accepting at least 2, right? How do I do that? Because I already know I'm keeping here means it is accepting at least 2. I keep all the strings in a lexicographical order because I can generate them using sigma star. Now epsilon I'll check accepted. I'll not wait because I'll run another thread. I'll check on A, I'll check on B. If any 2 threads are halting, then I'll stop, I'll put here. I'll stop all the threads because I don't need to run anymore. Similarly, all these Turing machines are halting at some point of time. The 2 threads are halting for each Turing machine. That is the reason I'm keeping here. Anyhow, logic exists for every Turing machine here. But what about its invalid strings of L? There is TM1, which is not accepting at least 2 strings. Means it might be 1 string or it might be no string. If it is no string, TM is accepting empty language. If it is 1 string, where already you have seen TM accepts only epsilon, that's only 1 string, right? Both the cases not RE. This has a logic, it will become RE but not recursive. Its complement is not RE. Its complement is what? When you have this RE but not recursive, no doubt L complement is what? Not RE. Now what is L here? RE but not recursive means you can choose this. No, yes, but be careful, sometimes I might be focusing on this, I am not focusing on this, be careful, okay? But we know this is the answer, RE but not recursive, we can choose this. If I miss anywhere, please be careful. When the answer is decidable, you can choose RE also. When the answer is RE but not recursive, you can choose RE also. Why? Because these 2 are present inside the RE class. So these languages are also called as RE language. TM halts after 2 moves. After 2 moves. Now, if suppose halts, right? Can you find out? This is a very, very interesting question. TM halts after 2 moves. It means TM does not halt within 2 moves. understand the same statement? TM halts means I don't know really halts, but I'm very clear TM does not halt within 2 moves. Can you verify this? Within 2 moves? Yeah, how many combinations are there? Finite. So this problem is very important. TM halts within 2 moves. You have a logic. Whether it moves or not, whether halts or not, you can easily check. S, every string that you have checked up to, within 2 moves means 2 length strings you can take up to 2 length. 0 length, 1 length, 2 length. For everybody you have proved that TM is not halting within 2 moves. You can say that TM halts after 2 moves. Halt doesn't mean that halt. It may never halt also. Remember that. TM halts after 2 moves means TM will never halt within 2 moves. That's the same statement. So this problem is very interesting. It's a decidable problem. It's a decidable problem. So it comes here, and no. Okay. So please take it as homework and work on it. Not easy to explain in a minute. So definitely you should spend much time to understand. TM halts within 2 moves. Previous problem only within 2 moves, right? That was does not halt. This is halt. Doesn't matter. Both are similar, right? So this is also decidable. Okay, decidable. Answer is TM halts within 2 moves. Is that for every string? That should be added, because I'm saying TM halts within 2 moves means for every string. I have not mentioned anywhere, right? Check for every string, is it halting within 2 moves? Then decide it. 15. How do you know that? You do not have the logic for only epsilon. You do not have the language of TM, just one language I'm talking about. Language has only one string. Now the language has many strings. Now I'm asking indirectly, the TM accepting regular. What proof I should give? I know TM accepts recursively enumerable. How do I know it is accepting CFL or not? Is it accepting regular or not? I'm not designing. Somebody is designed. How do I know? Verify. TM is unknown to me. And A star, how do I verify it? Only epsilon I am not able to verify on Turing machine. Only epsilon. This is straight away not RE. Okay. Very interesting problem. Not RE. Okay. It's definitely remaining fails. But if you have undecidable somewhere, if you have any option like this, choose that too. Undecidable. Because not RE means undecidable. Even RE but not recursive is also undecidable. Okay. So choose carefully. With this, we have completed our beautiful topic. I can say that most of the people who comes to the Turing machine, definitely they have to invest a lot of time. Today, very difficult to cover this many concepts in continuously within few hours, that too. I've tried my best to complete in one shot. In case you have doubts, I'm always there on this platform. You can come to app and you can ask doubts. Thank you so much. What I have explained in this video is about Turing machine, HTM and LBA, what they accept, and we have learned what is recursive language, what is recursively enumerable language, and apart from this, what is decidable and undecidable concept here. So many problems and languages we have looked at. Follow them. Some of the closure properties and some of the decision properties, all of them covered in this video. Okay. Thank you so much. In case if you have any doubts, please comment your doubts below this video, right? And also tag me once I see your doubt. I'll try to reply as soon as. Thank you so much. Bye bye. Take care.